Welcome, aviation enthusiasts and curious minds, to a journey through the skies like never before. We're about to embark on a thrilling exploration of the most unusual and innovative planes that defy the conventional norms of aviation. Originating from a design philosophy dating back to 1930, but conceived during the Second World War, the XCG-16 glider emerged as one of the most unconventional and innovative glider concepts ever tested. Initially designed for transporting heavy equipment and supplies, including vehicles and military personnel, the XCG-16 later became involved in experiments to deliver fuel to long-range bombers during flight. As a crucial element of the war effort, it showcased the capability to transport substantial loads without the need for an engine. Despite its troubled test history and eventual exclusion from production, the XCG-16's design retained its distinctive features. The roots of the XCG-16 can be traced back to May 1930, when American aero engineer Vincent Bernelli explored various lifting theories and flying wing concepts. The United States Army Air Force subsequently issued a specification calling for a novel design incorporating Bernelli's patented lifting fuselage concept. To assess the most suitable design for military use, a competition among different aircraft manufacturers was organized at Wright Field. Designers Hawley Bolus and Albert Kriz utilized Bernelli's concept as a foundation to create their own glider for the competition. Bolus, previously focused on designing leisure aircraft and recreational vehicles for the civilian market, ventured into military aircraft design for this competition. His most notable design had been the Bolus Road Chief, the trailer and caravan upon which Airstream had based their famous design. He'd also worked as one of the consultants on the Spirit of St. Louis, the aircraft piloted by Charles Lindbergh, who completed the first non-stop transatlantic flight between New York and Paris. Despite lacking experience in combat and military design, Bolus moved forward with his concept, collaborating closely with Kriz and the team at his company, Bolus Sailplanes. The German military's successful use of gliders during the 1940 invasion of Belgium, particularly in landing troops in challenging areas behind Belgian lines, drew attention. Gliders played a crucial role in capturing strategic sites, exemplified by the rapid overrun of Fort Aben-Amal in May 1940, where glider-borne Nazi soldiers surprised Belgian troops. While the United States initially maintained neutrality in the early stages of the war, experiences like the Battle of Fort Aben-Amal prompted the United States Army Air Corps to take gliders seriously into consideration. In response to the USAC's request for a glider capable of transporting troops, heavy equipment, and supplies towed behind engine-driven bombers and transport planes, Bolus and Kriz diverged from the traditional single fuselage design that characterized most American gliders. Instead, they embraced a flying wing concept, closely studying Bernelli's philosophy and incorporating their own ideas on top of it. A half-size prototype model was created in late 1942 by Bolus Sailplanes, with Bolus and his team considering the initial test results to be good. The first full-size glider prototype, named the MC-1 glider, was produced by General Airborne Transport. Following the closely followed design of the half-size model, initial factory tests once again indicated the potential of the new design. The full MC-1 design was envisioned to be larger than other gliders of its time. It was characterized by a high wing configuration with a wooden frame and fabric covering, all while retaining Bernelli's philosophy. With a wingspan of 110 feet and a length of 67 feet, the MC-1 boasted substantial dimensions. Bolus aimed for a cargo capacity of up to 15,000 pounds, facilitating the transport of both cargo and troops through two large cargo doors located at the glider's front for easy access and rapid deployment during battle situations. The intended operational method involved towing the XCG-16 into the air by a C-47 or C-54 Air Force transport plane, which would then release the glider to continue its flight independently. the glider featured a twin boom design for the tail. Designed with spoilers, the XCG-16 could deploy them to reduce lift and increase drag, enabling rapid descent and short landings on various terrains. Additionally, the glider was equipped with retractable landing gear, deployable for landings on rough ground. The maiden flight test of the MC-1 began on the 19th of July 1943 at March Field, California. The first test run proved to be a success and was commended by military and business observers. A second test flight was scheduled at March Field on the 11th of September 1943, but this run ended in disaster. Among the crew and passengers aboard the glider were notable aviator and businessman Richard Chichester DuPont and military glider specialist Colonel Ernest Gable, who was set to pilot the MC-1 for its demonstration. During the demonstration, the glider was towed by a Lockheed C-60. Shortly after takeoff, an unintended encounter with the C-60's prop wash caused the glider to violently sway from side to side. Compounding the issue, the weight ballast inside the glider had not been properly secured and began to shift, exacerbating the rapid tilting of the XCG-16. Recognizing that a crash landing was imminent, 3 of the passengers, including DuPont, attempted to parachute from the glider as it continued its descent. While 2 passengers successfully landed safely, DuPont tragically lost his life when his parachute didn't open in time. Colonel Gable remained on the glider and also lost his life when it ultimately crashed into the ground. Despite the tragic setback at March Field, Bolus continued with the design, and the US military awarded a contract to the General Airborne Transport Company in November 1943 after negotiations. The contract approved the construction of 3 MC-1 units. 2 flyable and 1 for static tests were awarded by the USAF. The completed full-sized MC-1 gliders were also given the military designation XCG-16, and the name stuck. Only 1 completed XCG-16 unit was manufactured and submitted for USAC testing. Test pilots and engineers acknowledged the XCG-16's strong aerial performance, highlighting its excellent stability and maneuverability. However, military observers concluded that the glider fell short of expectations in terms of cargo and loading capabilities, deeming it unsuitable for combat situations. Consequently, no additional units were produced. There was initial consideration of repurposing the glider for new Air Force experiments. In 1944, the US military explored the concept of extending the range of existing transport and bomber aircraft by utilizing trailing gliders to carry fuel. The XCG-16 airframe was handed over to the Cornelius Aircraft Company, known for building gliders, to modify and test the forward-swept wing design, capitalizing on the XCG-16's robust capabilities. The Cornelius Company made several alterations to the glider, renaming it the XFY-1 and prepared it for a test flight. However, the first XFY-1 model crashed during a demonstration in October 1944. Although a second model was produced by Cornelius following the Bolus format, by that time the US military had lost interest in the project, leading to the discontinuation of further development. Throughout the 1950s, major aircraft manufacturers in the United States were eagerly exploring the potential of vertical takeoff and landing (VTOL) technology across various military applications. With the looming threat of intercontinental ballistic missiles and thermonuclear weapons, the military sought VTOL aircraft capable of operating from small dispersed sites without relying on traditional air bases or aircraft carriers, targets that were increasingly vulnerable to attack. A key concept driving this pursuit was the notion that an aircraft with a thrust-to-weight ratio exceeding 1 could vertically launch, transition to horizontal flight for mission execution, and then return for a vertical landing. Such capabilities promised to eliminate the need for expensive and easily targeted runways, enhancing the aircraft's survivability and operational flexibility in a rapidly evolving strategic landscape. Among the pioneers in this endeavor was the Ryan Aircraft Corporation, which endeavored to translate this concept into a practical fighter aircraft for the Air Force with its X-13 Vertijet. However, like most other VTOL aircraft, the performance compromises made for their unique capabilities did not warrant its introduction in place of more capable conventional aircraft. The idea for the Vertijet originated just after World War II, when engineers for Ryan casually debated whether or not their FR-1 Fireball, which had a thrust-to-weight ratio of 1 at low fuel quantities, could take off vertically. The vertical takeoff idea soon advanced beyond the discussion stage. In 1947, the Navy's Bureau of Aeronautics enlisted Ryan for a contract aimed at exploring the technical complexities associated with developing a vertically launched jet fighter, a pivotal aspect of a broader initiative to assess the viability of submarine-based aircraft. Concurrently, the Navy funded a series of experimental tail-sitter aircraft comprising conventionally configured planes outfitted with large counter-rotating propellers designed to rest vertically on reinforced tail sections. Notable examples included the Convair XFY-1 and Lockheed XFV-1, intended to utilize their high-thrust propellers for vertical takeoff from various naval vessels, thereby furnishing defensive air cover without the need for aircraft carriers. Ryan's engineering analyses demonstrated the feasibility of a comparable jet-powered design, augmented by a reaction control system capable of redirecting exhaust gases to facilitate control during hovering and low-speed flight. Subsequently, a Navy contract facilitated the construction of an unmanned flying prototype, which conducted its inaugural flight on October 20, 1950. This peculiar contraption, affectionately dubbed the Beast in the Backyard, was propelled by an Allison J33 turbine and employed a ball-mounted nozzle to provide reaction control while hovering. Ryan engineers converted a B-47 fuel tank into a cockpit to allow test pilot Peter Girard to evaluate the testbed's suitability as a manned research aircraft, which sat on its tail to take off vertically. On November 24, 1953, Girard made the first manned hovering flight in a jet aircraft with this unusual machine. After Navy funding ran out, the Air Force became interested in Ryan's experiments and in July 1954 issued a contract to the company to construct 2 VTOL tail-sitter demonstrators, designated as the X-13 Vertijet. This project, based on the earlier Navy design proposal, was to demonstrate the suitability of easily dispersible VTOL fighters. Under the guidance of Chief Engineer Curtis Bates, the X-13 emerged as a compact, single-engined delta-wing fighter, with its distinctive features being a set of winglets and fixed landing gear, elements that might appear ordinary to the casual observer. Spearheaded by Robert Furman and the Ryan Technical Section, the aircraft was meticulously designed to be transported on a specialized trailer, capable of tilting vertically to facilitate the launch and recovery of the X-13 during vertical takeoffs and landings. In late 1955, Ryan successfully completed the first Vertijet, serial number 541619, and on December 10th, Girard piloted its maiden flight. Initially equipped with a fixed tricycle landing gear, the X-13 underwent testing as a conventional aircraft. Furman and his team prioritized exploring the conventional handling characteristics before risking vertical flight testing. Following the resolution of oscillation issues through the installation of dampers, engineers affixed a temporary steel tube truss with custering wheels to the rear of the X-13. This modification allowed the aircraft to assume a tail-sitting position during vertical flight testing, eliminating the need for the complex launch and recovery procedures associated with the launch trailer. Pete Girard made the first vertical takeoff and landing on May 28, 1956. On the same day, the second X-13 made its first flight. The aircraft was agile and responsive in conventional flight. As the aircraft transitioned to a nose-high attitude to achieve a hover using the thrust from its own engine, a vectorable exhaust nozzle linked to the controls provided a straightforward and efficient means of control. To facilitate the delicate landing process, small bleed air thrusters positioned on the wingtips enabled minor adjustments to the pitch and yaw of the aircraft when necessary. Integrating both conventional and VTOL control systems, a stability augmentation system ensured smooth transitions without requiring abrupt changes to pilot control inputs. During vertical takeoff, the launch procedure involved raising the bed of the launch trailer vertically. This allowed the X-13 to hang from a cable suspended by two arms on the top of the trailer, featuring a partially retractable hook. For vertical operations, flat bumpers replaced each of the main wheels on the fixed landing gear, preventing damage to the fuselage underside if it swung into the trailer bed, thereby facilitating transportation. Subsequently, the pilot would increase throttle until the hook lifted off the launch cable, then maneuver away from the trailer and accelerate vertically, smoothly transitioning to conventional flight. However, vertical landings posed greater challenges and were perhaps the most impractical aspect of the Vertijet concept. Its primary drawback, akin to earlier tail-sitters, lay in the obstruction of the pilot's vision by the airframe, making it exceedingly difficult to accurately gauge the distance to the ground without external assistance. Although the pilot's seat pivoted 45 degrees towards vertical during landing, the pilot still had to approach the recovery trailer blind, with the underside of the fuselage facing the surface of the trailer. Constant radio communication with a ground observer was essential to talk the X-13 into position during the cumbersome process. A 6-meter, 20-foot long folding pole with marked gradations attached to the top of the recovery trailer gave the pilot a clear indication of the distance remaining before he contacted the trailer. Once in position, the pilot gradually reduced the throttle until the nose hook caught the recovery cable. On May 28, 1956, the X-13 executed its inaugural vertical hovering flight, initiating a series of summer tests where Girard and fellow test pilot Lou Everett practiced cable catching techniques using a 1-inch thick rope strung between two towers. To safeguard against potential damage during docking maneuvers with the trailer, Ryan engineers equipped the X-13 with a replaceable wooden nose. On November 28th, Girard accomplished the first ever transition from horizontal to vertical flight and vice versa in the X-13. Then on April 11th, 1957, he launched from the trailer, seamlessly transitioning to conventional flight and executed a vertical landing, successfully fulfilling the X-13's mission profile. Illustrating the concept of dispersed operating sites, the second X-13 captivated over 3,000 military officers and journalists with an impressive display at the Pentagon on July 30th, 1957. However, competing programs diverted funds away from the project, leading to the X-13's final flight on September 30th, 1957. Despite later programs like the XV-6 Kestrel and the AV-8 Harrier achieving operational success, the X-13 provided an effective solution to the challenges of developing a VTOL fighter within the technological constraints of its era. The Vertijet successfully completed all designated tasks and undoubtedly excelled as an experimental demonstration aircraft, despite the inherent impracticality of the operational concept. Ironically, by the close of the 20th century, the thrust vectoring system, originally pioneered on the X-13, would evolve into an indispensable component of advanced combat aircraft. In 1960, Ryan generously donated the first X-13 along with its launch trailer to the Smithsonian Institution. The idea of a jet-powered seaplane fighter had intrigued military aircraft engineers since the conclusion of World War II, leading to numerous attempts to bring this concept to fruition. The envisioned aircraft was to be powered by jet or rocket propulsion, possessing the capability to take off and land on water while maintaining fighter-like qualities in the air. The strategic allure of such a concept was significant. It promised a versatile fighting force with the ability to deploy anywhere globally, stationed until required, a cost-effective alternative to a lingering aircraft carrier. The rapid ascent to the skies endowed it with the capability to swiftly intercept marauding enemy forces. To address these challenges, the US Navy commissioned the development of several subsonic fighters. Valid concerns were raised, as many supersonic designs of the era exhibited drawbacks such as lengthy takeoff rolls, high approach speeds, and instability, particularly problematic for carrier operations. The Sea Dart was a prototype single-seat fighter designed and built by the Convair division of General Dynamics Corporation at San Diego, California. It was equipped with retractable skis in place of ordinary landing gear to allow it to take off and land on water, snow or sand. When stationary or moving slowly in the water, the Sea Dart floated with the trailing edge of the wings touching the water. The skis of the aircraft were deployed once it reached a speed of approximately 10 miles per hour during its takeoff run. Convair's Sea Dart proposal secured an order of 2 prototypes in late 1951, with an additional 12 production aircraft ordered even before a prototype had taken its maiden flight. While no armament was installed on any Sea Dart, plans included fitting the production aircraft with 4 20mm Colt Mark 12 cannons and a battery of folding fin unguided rockets. 4 of these initial orders were redesignated as service test vehicles, and an extra 8 production aircraft were promptly added to the order. The necessary power was generated by a pair of afterburning Westinghouse XJ46WE02 turbojets, drawing air from intakes positioned high above the wings to avoid ingesting spray. In the absence of these engines for the prototypes, twin Westinghouse J34WE32 engines with just half the power were temporarily installed. The prototype initially featured an experimental single ski, which demonstrated greater success compared to the twin ski design of the second service test aircraft. Testing with several other experimental ski configurations continued with the prototype through 1957, after which it was placed into storage. The US was not the only country to consider the hydroski. The Saunders Roe Company of the United Kingdom, which had already built an experimental flying boat jet fighter, first flying in 1947, the SRA-1, tendered a design for a ski-equipped fighter, but little came of it. In the 1950s, the US Navy considered the internal arrangements of a submarine aircraft carrier that could carry 3 of these aircraft. Stored in pressure chambers that would not protrude from the hull, they would be raised by a portside elevator just aft of the sail and set to take off on their own on a smooth sea, but catapulted aft in a higher sea. The program only reached the writing on a napkin stage, for 2 problems were not addressed. The hole for the elevator would have seriously weakened the hull, and a load of a laden elevator would also be difficult to transmit to the hull's structure. Constructed at Convair's San Diego facility at Lindbergh Field, the aircraft underwent testing in San Diego Bay in December 1952. Piloted by ED Sam Shannon, an unintended short flight occurred during what was initially intended as a fast taxi run on the 14th of January 1953, with the official maiden flight taking place on the 9th of April. The fighter, powered by underwhelming engines, exhibited sluggish performance. The hydroskis, despite being extended on shock-absorbing oleo legs, caused violent vibrations during takeoff and landing. Although modifications to the skis and legs somewhat improved the situation, the issue of sluggish performance persisted. The Sea Dart, equipped with J-34 engines, failed to achieve supersonic speed in level flight, hindered by its pre-area rule shape, leading to higher transonic drag. Consequently, the second prototype was cancelled, and focus shifted to the first service test aircraft, outfitted with J-46 engines that fell short of specifications. However, during a shallow dive, speeds exceeding Mach 1 were reached with this aircraft, making it the only supersonic seaplane to date. On the 4th of November 1954, Sea Dart Bu number 135762 disintegrated in mid-air over San Diego Bay during a demonstration for naval officials and the press, killing Convair test pilot Charles E. Richbourg when he inadvertently exceeded the airframe's limitations. Even prior to this tragic event, the Navy's interest in the Sea Dart program had been waning. The crash further downgraded the program to experimental status. Consequently, all production aircraft were cancelled, though the 3 remaining service test examples were completed. The last 2 prototypes, unfortunately, never took to the skies. The Grumman X-29, an experimental aircraft featuring a forward-swept wing design, marked a significant breakthrough in aeronautical innovation. Prior to the X-29, various attempts had been made to explore the concept of forward-swept wings, including NACA's wind tunnel tests in 1931 and the German Junkers JU287 during World War II. However, these experiments faced challenges related to aeroelasticity, as the available technology and materials were inadequate to prevent wing deformation. The turning point came in the early 1960s, with the development of the Hansajet HFB-320 by Hamburger Flugzeugbau in Germany. This civilian jet, certified in 1964, became the first aircraft with forward-swept wings to use them successfully. The key to overcoming aeroelastic issues was the utilization of lightweight and exceptionally strong composite materials, which became available in the 1970s. These materials allowed for the construction of wings that could resist deformation under aerodynamic forces. In this context, the Grumman X-29 emerged as a groundbreaking experimental aircraft that validated the feasibility of forward-swept wings. The X-29's design aimed to explore the advantages and challenges associated with this wing configuration. Despite initial skepticism, the X-29 demonstrated remarkable efficacy and became an unexpected success in aviation history. Its innovative design and successful flight tests contributed valuable insights to the field of aeronautics. In the 1970s, the emergence of composite materials, which were extremely light but stronger than conventional materials, further encouraged engineers to pursue this unusual line of inquiry. In 1977, the Defense Advanced Research Project (DARPA), together with the U.S. Air Force Flight Dynamics Laboratory at Wright-Patterson Air Force Base, Ohio, authorized a program to study this novel wing concept and to confirm with scientific precision the findings of other studies, which had claimed it led to better control and lift qualities during extreme maneuvers, that it reduced aerodynamic drag, and that it flew more efficiently at cruise speeds. The Grumman X-29 project marked a significant development in aviation, with Grumman Corporation being selected as the project lead in December 1981 and receiving $87 million to produce 2 prototypes. The official unveiling of the X-29 took place on August 27, 1984, at the Grumman facility in Culverton, New York. Grumman Corporation President George M. Skurla emphasized the aircraft's importance in expanding the frontiers of manned flight and investigating new technologies for future generations of more agile, fuel-efficient, and cost-effective tactical aircraft. Key specifications of the X-29 included a length of 16.44 meters, a height of 4.26 meters, an empty weight of 6,260 kilograms, and a maximum weight of 8,074 kilograms. The aircraft was powered by a single General Electric F404 GE400 engine, enabling it to achieve a top speed of Mach 1.87, a range of 560 kilometers, and a maximum altitude of 50,000 feet. The X-29's design and capabilities were geared towards exploring new technologies in flight, contributing valuable insights to the advancement of future aircraft. This project represented Grumman's commitment to pushing the boundaries of aviation and embracing innovative solutions for improved performance and efficiency. The X-29's aeroelastic tailored wing added even more stabilization by preventing structural divergence from happening within the flight envelope. Moreover, some measure of artificial stability was added by an electronic triple-redundant digital fly-by-wire flight control system, which made up to 40 commands per second to adjust the control surfaces where necessary, since the wing design was naturally highly unstable. The Grumman X-29 featured several innovative design elements aimed at enhancing its flight control and aerodynamic performance. The use of forward canards, positioned in front of the wings, served as primary flight control surfaces, primarily providing pitch control. Additionally, strake flaps located on either side of the rudder contributed to pitch control. Roll control, on the other hand, was achieved through flaperons, which were a combination of flaps and ailerons, modifying the wing camber. The wing trailing edge actuators responsible for controlling camber were intentionally mounted externally in streamlined fairings due to the thinness of the supercritical airfoil. The supercritical airfoil itself, a component first developed in the 1970s with F-8s, had a flatter upper wing surface to reduce the power of incoming shockwaves, resulting in decreased drag. To optimize costs, the X-29 utilized undercarriage components borrowed from the F-16, including anti-skid tires and carbon brakes. The fuselage and nose wheel were sourced from F-5As, with one previously serving in the USAF and the Norwegian Air Force. In September 1984, the No. 1 X-29, after routine taxi tests, had its F-404 engine removed, was protected with a blanket, and transported via ship from Bayonne, New York, through the Panama Canal to San Pedro, California. From there, it was taken to Edwards Air Force Base. On December 14, 1984, the first version of the X-29 commenced Phase 1 flight testing. Throughout 242 test runs, evaluators observed that at moderate angles of attack, the wingtips didn't stall due to the air moving over the forward wing inwards rather than outwards. These flight tests provided valuable insights into the aircraft's aerodynamic behavior and performance characteristics. Accident-free flights also revealed the merits of the stabilization measures put into place to counteract the highly unstable forward-swept wing, with pilots consistently reporting good handling characteristics. In fact, one such pilot, Chuck Sewell, enjoyed flying it so much that during the opening round of test flights, he asked ground control permission to enter it into a roll. On May 23, 1989, the second version of the X-29 commenced Phase 2, consisting of 120 flights. The primary objective of this phase was to explore the high angle of attack characteristics of the aircraft and assess potential military applications of a forward-swept wing configuration. While the No. 1 X-29 had operated at a 21-degree angle of attack, the No. 2 was flown at a significantly higher 67 degrees. Surprisingly, the aircraft exhibited exceptional maneuverability and control that exceeded all expectations, surpassing predictions from computer models. At 45 degrees, the X-29 displayed excellent control characteristics, and even at the extreme angle of 67 degrees, it retained limited controllability. This unexpected phenomenon was attributed to the forward-swept wing design. Notably, the aircraft demonstrated effortless control without the need for leading edge flaps on the wings to provide additional lift. Additionally, there was no requirement for movable vanes on the engine's exhaust nozzle to alter thrust direction under such conditions. These findings highlighted the remarkable performance capabilities of the forward-swept wing configuration. Although the X-29 hadn't reduced aerodynamic drag as previous studies had attested, it did show the benefits of several novel devices, such as the aeroelastic tail and the close-coupled canard for longitudinal control, while proving possible that with the right design, high angle of attack control could be achieved. It was this last breakthrough that would persuade policymakers to employ it in one last experiment. In 1992, the No. 2 Grumman X-29 was enlisted by the Air Force to participate in a program exploring the implementation of Vortex Flow Control (VFC) at a high angle of attack to maintain control, overriding normal flight control systems. The X-29 underwent modifications, incorporating two high-pressure nitrogen tanks linked to small nozzle jets in the forward upper portion of the nose. The purpose was to pump air into the vortices generated off the nose during high angles of attack. The modified X-29 engaged in a series of over 60 flights between May and August 1992 to assess the practicalities of VFC. The system, previously tested at the Air Force's Wright Laboratory, demonstrated that injecting air into the vortices altered their flow direction, generating the forces necessary to change the nose's direction. This became particularly advantageous at higher angles of attack, where traditional control surfaces like the rudder lost effectiveness. The assessment revealed that VFC allowed the aircraft to move left and right with relative ease at higher angles of attack, compensating for the limitations of conventional control surfaces. However, VFC had its drawbacks. It couldn't impose control on the presence of side winds, and it didn't eliminate consistent oscillation. Currently, the second X-29 is on display at the Dryden Flight Research Center, while the first is exhibited at the Air Force Museum. In 2004, renowned director Martin Scorsese released the feature film The Aviator, which garnered 5 Oscars. This cinematic masterpiece sparked widespread interest in one of America's most extraordinary figures, billionaire Howard Hughes. Among his many ventures, Hughes undertook the ambitious project of creating a colossal amphibious aircraft known as the Hughes H-4 Hercules. This flying boat, constructed as a singular prototype, made its historic maiden flight on November 2, 1947. Despite only completing a single flight, Hughes's Hercules secured its place in history as the largest flying boat ever built. Its monumental wingspan of 98 meters remains unrivaled to this day, surpassing even the dimensions of aircraft such as the AN-124 Ruslan and the AN-225 MRIA. During the early stages of World War II, Allied forces initially underestimated the threat posed by Nazi Germany's submarines. Lessons from World War I had been disregarded, leading to catastrophic losses in naval trade. While losses from German submarine attacks were initially manageable during 1939 to 1940, the situation escalated dramatically in 1941 to 1942. The German Kriegsmarine unleashed a reign of terror across the vast expanses of the Atlantic, sinking nearly 700 Allied ships in the first 7 months of 1942 alone. It wasn't until the latter part of 1942 that the situation in the Atlantic began to improve, primarily due to a significant increase in the number of escort ships deployed to protect convoys. This concerted effort helped mitigate the threat posed by German submarines, albeit after considerable losses had already been incurred. Despite these actions, the threat from German submarines was not eliminated. In such conditions, the idea was born that would protect valuable military goods from Kriegsmarine attacks. Cargo could be shipped across the Atlantic Ocean not only by water, but also by air. However, the implementation of this idea would only be possible with the creation of a transport plane of sufficient carrying capacity. To address the pressing need for a solution, shipbuilder Henry Kaiser proposed the design of a large transport flying boat. Renowned billionaire and aircraft designer Howard Hughes enthusiastically took on the challenge of bringing this concept to fruition, resulting in the creation of a giant aircraft that remains unparalleled to this day. In 1942, the US government contracted Howard Hughes to construct a single prototype aircraft, driven by the vision of a sizable flying vehicle to support naval operations. The result was a multi-ton wooden amphibious aircraft with a remarkable wingspan of almost 100 meters. Initially designated as the NK-1 Hercules, this flying boat boasted impressive dimensions that continue to impress. A fuselage spacious enough to accommodate over 700 soldiers, weaponry, and approximately 60 tons of commercial cargo. To provide the necessary power for this colossal aircraft, 8 engines were installed in its wings. The project's development was guided by a specific goal: to construct an aircraft for cargo and passenger transportation while minimizing the use of strategic raw materials. Consequently, the decision was made to build the aircraft from wood rather than aluminum. The envisioned role for this flying boat was to transport troops and various cargoes from the United States to war-torn Europe along a secure air route, circumventing the threat posed by the German submarine fleet. Working documentation for the new flying boat was developed very quickly, which cannot be said about the pace of the aircraft construction itself. The works that began in 1943 were fully completed only by the middle of 1947. This slowdown in the construction of the aircraft was influenced by several reasons, ranging from the end of the Second World War, as a result the military lost interest in this car, and ending with various legal proceedings against Howard Hughes. Disputes regarding the funding for the project persisted throughout its execution, reflecting differing opinions on its necessity. One dissatisfied US senator famously referred to the future amphibious aircraft as a flying forest warehouse, but it garnered another well-known nickname, the Spruce Goose. A substantial sum from the US state budget, totaling $22 million, a considerable amount for the time, was allocated for the project's implementation. However, this funding proved insufficient, prompting Howard Hughes to personally invest an additional $18 million into the endeavor. The flying boat, subsequently renamed the N4 after Henry Kaiser's departure from the project, marked the fourth aircraft of Howard Hughes's own construction. On November 2, 1947, the N4 made its inaugural and final flight, piloted by Hughes himself. The aircraft undertook a brief flight, ascending to an altitude of 21 meters and traversing a 2-kilometer stretch along the coast of Los Angeles. With this flight, the saga of the Hercules nearly came to a close, transitioning abruptly from the realm of active aviation to that of a museum exhibit. Ultimately, this costly and sizable flying boat proved to be of little practical use at the time. The Hughes H-4 Hercules was characterized by a hull, a cantilever wing, and 8 radial engines. The flying boat had a vertical and tail plumage, as well as fixed wing floats. The entire structure of the aircraft consisted of laminated wood, but contrary to the nickname in the construction of the flying boat, it wasn't spruce, it was birch. At the Howard Hughes plant, woodworking was able to achieve high aviation standards. The construction of the aircraft involved creating full-size patterns of structural elements, from which matrices were produced for molding the parts. The thinnest piece, with a thickness of 1.2 mm, consisted of 3 layers, each 0.4 mm thick. Conversely, the thickest part measured 254 mm in thickness and comprised 200 layers of veneer, each 1.27 mm thick. To maintain the integrity of the veneer layers during gluing, double-capped nails were utilized. Once the glue had set, these nails were removed using a special nail puller, resulting in the extraction of approximately 8,000 nails across the entire flying boat. The resulting holes were then sealed with a specialized putty. Following assembly, a thin layer of primer was applied to the surface, succeeded by a layer of rice paper and 2 coats of protective lacquer. The exterior surfaces of the aircraft were coated with aluminum paint, concealing the fact that the aircraft's underlying structure was composed of ordinary wood. Both the aircraft's skin and its structural components appeared as if they were made of aluminum. The cargo compartment of the amphibious aircraft featured 2 levels, interconnected by a spiral staircase. Hinged doors located at the nose of the aircraft facilitated the easy passage of 2 railway cars or a Sherman M4 tank. This design ensured the versatility and practicality of the aircraft for transporting various types of cargo. At that time, the Hughes H-4 Hercules was the only aircraft that was able to transport the tank through the air. In the best traditions of submarines and ships, 18 seal compartments were provided in the design of the seaplane. 6 of them were enough to keep it afloat. The electrical equipment of the aircraft operated from direct current with voltage 120B, since with traditional 24B, the cross-section of the wires, the length of which reached 50 kilometers, was very large. The seaplane was to be lifted into the air by 8 huge radial air-cooled R4360 Wasp major piston engines from Pratt & Whitney. Each of these engines developed 3,000 horsepower. The engines of the aircraft were equipped with 5-meter 4-blade propellers. Of the 4 engines positioned closest to the fuselage, 4 were capable of generating reverse thrust, granting the giant aircraft the remarkable ability to maneuver independently in reverse and execute tight turns. The expansive size of the flying boat facilitated in-flight engine repairs, as special passages within the enormous wing allowed access to the engines. At the point of attachment to the fuselage, the wing section reached a height of 4 meters. Despite its unprecedented scale, only a crew of 3 individuals was required to operate the aircraft. The collaborative effort between Hughes and Kaiser aimed to produce the largest aircraft ever constructed, surpassing any previous aircraft in size by a staggering 7-fold. This ambitious project stands as one of the most remarkable endeavors in aviation history. The determination and valor of Howard Hughes and his dedicated team, who persevered despite numerous challenges, culminated in the historic flight of the H-4 Hercules. However, tensions arose within the project leadership, leading to significant contradictions. Henry Kaiser advocated for the construction of a 70-ton aircraft to adhere to deadlines and present a finished product to the military. Conversely, Howard Hughes insisted on building a 200-ton airplane, necessitating greater investment of time and resources. This discord ultimately led to Kaiser's departure from the project, while Hughes became increasingly enamored with the idea, incorporating new improvements and proposals that further prolonged the construction timeline of the flying boat. As a result, in 1942, this order was urgent for the US government, but by 1944 it lost its relevance. By this time, the situation on the fronts of World War II had changed radically, and the interest of the United States in the project gradually faded away. The US government had contemplated cancelling the contract for the seaplane's construction, but by then, Hughes's motivation had transcended mere practicality. He had become consumed by the idea of creating a cargo aircraft that would surpass even the most extravagant imaginations of his contemporaries. On November 2, 1947, the Hercules was launched, and Hughes, alongside his small crew, initiated the aircraft engines for the first time. Following several water taxi tests in front of a sizable audience, predominantly journalists, the flying boat lifted off from the surface of the Los Angeles harbor without any prior announcement, embarking on its inaugural and final flight. Maintaining an altitude not exceeding 20 meters, the Spruce Goose traversed approximately 2 kilometers at a speed of 120 kilometers an hour before executing a flawless landing. This unauthorized test flight, undertaken in defiance of an official ban on taking the plane airborne, served to silence numerous critics of the project, demonstrating that the largest aircraft in history was indeed capable of flight. Many regard this flight as one of the most significant moments in the annals of aviation history. Following its historic flight, the Spruce Goose returned indefinitely to its hangar, a colossal structure specially constructed to house it and prevent it from ever taking flight again. At Howard Hughes's behest, until his passing in 1976, the flying boat remained in a state of perpetual readiness, with its engines started every month. Initially, a team of 300 individuals monitored the aircraft's condition until the 1950s, when the staff was reduced to 50 people. Nevertheless, the annual cost of maintaining the air giant in flight-ready condition amounted to approximately $1 million. Additionally, the construction of the hangar where the Hughes H-4 Hercules was preserved for eternity incurred costs of around $2 million. Currently, this unusual aircraft is an exhibit at the Aviation Museum in McMinnville, Oregon, where it was transported in 1993. At the same time, over the past 50 years, this flying boat has become one of the most beloved artifacts of the United States, moving from a state of almost total uselessness to the category of object of cultural heritage. Today, the story of the Hughes H-4 Hercules, which soared into the sky only once in its lifetime, is revered as a testament to its creator's unparalleled resolve to see the project through to completion, transforming the aircraft into an emblem of the 20th century. Regarded as a symbol of determination and ingenuity, the Spruce Goose continues to captivate the imaginations of people worldwide. Drawing over 300,000 visitors annually, the aircraft stands as a living testament to Howard Hughes's extraordinary vision and perseverance. Its towering presence serves as a reminder of the boundless ambition and unwavering commitment that characterized an era of pioneering aviation endeavors. Through its enduring legacy, the Hughes H-4 Hercules remains an enduring symbol of human achievement and innovation. So many of the ingenious designs for aircraft put to paper throughout history never came into production or often died at the prototype stage. Some of these aircraft became conceptual legends, and others were instead renowned for their absurdity. The Bartini Biriev VVA-14 is a bit of both, not least because of its purpose and the colourful inventor behind its design. Perhaps the best means of understanding the genius behind the plane is to understand the genius behind its creator, Roberto Bartini. Bartini was born in the infamous city of Fiume, in what was then Italy and is currently modern-day Croatia. He would live through the early part of the 20th century through political uproar and the reorganization of states and borders that took place as a result of the First World War. He showed a passion for aviation early on in life, and more specifically for innovative aircraft designs and concepts, a passion which would lead the Italian engineer to the Soviet Union. After studying engineering at the ancient and world-renowned University of Bologna, often recognized as the Oxford of Italy, he joined the revolutionary aircraft manufacturer Caproni, where he worked alongside his mentor, the creative genius Giovanni Caproni. During his time at Caproni, Bartini was instrumental in making key innovations and design improvements in a number of the company's aircraft. However, Bartini's life would change completely when he was offered the opportunity to participate in aeronautical research in the Soviet Union. Fascinated by the career opportunities and prospects, Bartini accepted the offer. However, his decision to leave Italy was layered. Post-World War I Italy was politically and economically unstable. Furthermore, Bartini was an avid socialist and felt that the Soviet philosophy of strongly supporting scientific innovation would create potential for significant advancements in new aircraft technologies. From the moment Bartini arrived in the Soviet Union, he found himself directly involved in a variety of important projects. He began research at the Central Aero Hydrodynamic Institute, known by the acronym TSAGI, in Moscow, where he contributed greatly to a number of aircraft designs and concepts. However, Bartini had a knack for innovation and showed a notable prowess in engineering that made him stand out compared to his colleagues. He was quickly recognized for his notable mind when it came to aeronautics. His creativity and inventiveness earned him a reputation as a man with an unconventional but effective approach to aircraft design. Before he even began work on the Bartini Beriev, he designed the Bartini Stal 7, an elegantly designed twin-engine flying-wing transport aircraft, which would act as an inspiration for the Year 2 and the Year 4. Although the plane never went into production, it displayed the Italian engineer's uncanny ability to bring unconventional aircraft designs to life in a manner that similar engineers of his day were unable to do at the time. During the 1930s, Bartini began researching what would be the genesis of his masterpiece, the Bartini Beriev VVA-14 submarine hunter. Bartini began researching seaplanes and amphibious aircraft for their dual civilian and military applications. His early designs made use of retractable landing gear and hulls which were optimal for waterborne operations. Bartini's seaplane concepts were seen as impressive for their time and earned him significant status amongst his peers. World War II would see Bartini's expertise come to center stage. His contributions were essential to the Soviet Union's war effort. His experience was put to use on a myriad of projects, which included strategic bombers and reconnaissance aircraft. While Bartini's career was ultimately marked with success during his time in the Soviet Union, he did experience difficulties in his personal life. He underwent uncomfortable periods of political scrutiny and surveillance during the iron-fisted years of Stalin's regime. Yet Bartini managed to navigate the complex maze of Soviet politics and ultimately preserve his position as a respected aeronautical engineer. The apex of Bartini's career will be his work on the Bartini Beriev VVA-14 submarine hunter, a conceptual design which he began work on in the late 20th century. Even by today's standards, it was a marvel of engineering and design, capable of landing on any surface and taking off from any position. Known in Russia as the Vertikalno Vzletayashaya Amphibia or vertical takeoff amphibious aircraft, the VVA-14 was a highly experimental plane developed by the Soviet Union. It was intended to harness the abilities of a high-velocity aircraft combined with those of a seaplane. It also took advantage of the ground effect, compressing air in order to create a cushion between it and the water, meaning it could effectively function as a ship if needed. The question remains, why did Moscow want Bartini's airplane design to have so many different capabilities? The answer? Anti-submarine warfare, or ASW for short, and who better to design such a plane than one of the foremost amphibian aircraft experts in the world? The project began in the 1960s. Its scope was to create a submarine hunting aircraft that could operate in vastly different environments, from remote areas to coastal regions and large bodies of water. The VVA-14 had a uniquely long range and the ability to fly at unusually high speeds while carrying a large payload of radar equipment and other reconnaissance technology. The VVA-14's central fuselage extended forwards and backwards, housing the cockpit and engines. The wings were mounted above the fuselage with two pontoons directly beneath them. The pontoons not only allowed for water takeoffs and landings, but also provided extra fuel storage and contained regular landing gear as well. Perhaps the most impressive aspect of the plane, especially at the time it was conceived, was its VTOL functions. The VVA-14 used a special propulsion system to enable this. The plane came with two separate engine types, lift engines and cruising engines. The lift engines were located in the fuselage and could rotate to create vertical thrust for sustained hovering and VTOL capabilities. The engines responsible for lift were typically turbo engines, like the Kolesov RD-36-35, and they were potentially capable of producing a titanic 8,800 pounds of thrust. Horizontal flying relied on turbofan cruise engines in the fuselage, like the Lyalka AL-7F. These engines produce a whopping 20,000 pounds of thrust. Different prototypes of the VVA-14 varied in the quantity of these engines used. Once finally in flight, the VVA-14's wings would rotate into position and the lift engines would reposition into a horizontal configuration. The cruise engines would then take over the forward flight function. The VVA-14's VTOL capability would have made it ideal for operating in extremely unconventional environments where other planes couldn't actively take off and land, such as bodies of water. This functionality also made the aircraft highly fuel efficient. The plane had channels which directed air beneath it, creating a cushion or gap which effectively allowed the VVA-14 to act as a hovercraft and therefore ship on the water. Overall, the plane's test runs were not unpromising. It reached an impressive top speed of 550 km an hour for a plane of its size, and water taxiing proved relatively successful. Perhaps most notably of all was the plane's odd design. Aside from being a truly hulking vehicle, it looked extremely modern for its time. The VVA-14 looked more like a comic book spaceship than a conventional airplane, with its back-mounted boosters and W-shaped body. This unique aesthetic was typical for Bartini's aircraft, which often sat at the cutting edge of aeronautical design. The conceptual outlines for the Beriev BE-1 and the Beriev BE-2500 reflected the very same ingenuity and prowess. Bartini's concept was undoubtedly a theoretically perfect answer to an increasingly hard-fought war against submarine technology. However, his prototype airplanes did not come through without their significant challenges and technical problems. One major issue was the plane's VTOL flight. The batteries needed to power the lift engines were never delivered, therefore the Kolesov RD-36-35 was never used to help the plane take off or land vertically. The aircraft's highly complex design led to stability and control problems. Its unconventional configuration, using a variety of different engines, resulted in an inability to reach optimal stability. Furthermore, the plane's complexity meant maintenance was a nightmare. The engine's swiveling mechanisms added yet another layer of difficulty to properly maintaining and repairing the plane, all while raising the number of potential points of failure. And like any project, the VVA-14 suffered from budgeting issues. The cost of developing and testing the aircraft required multiple expensive prototypes, and Bartini's innovations, while genius, were extremely costly. Ultimately, the VVA-14 sucked up more resources than could be appropriately allocated to it. This is in part what led to the project's cancellation, especially given that the increased funding needed could not be justified against other Cold War expenses. In the end, priorities in the military were changing, and the Soviet Union and Navy decided to focus on an entirely different type of aircraft. The project was slowly deprioritized and cancelled. Bartini's submarine hunting beast never saw operational duty and ultimately fell to the wayside, ending up in a museum of aeronautics in Moscow, a shell and memory of the tireless work that went into creating an entirely new species of aircraft. However, despite the plane's ultimate failure as a project, Bartini's innovations and concepts were some of the most riveting and impressive for their time. He remains one of the earliest proponents of VTOL flight, and his designs are still unconventional and highly avant-garde by today's standards. Roberto Bartini knew how to push boundaries in a way that made him truly unique. His multidisciplinary approach incorporated disciplines from hydrodynamics to biomimicry. he turned to every source of inspiration he could in designing his planes. Perhaps that's why they were so futuristic. Maybe Bartini's VVA-14 went the way of all truly genius designs. Perhaps it was too far ahead of its time. Shining a light on his ideas means his legacy can go on, and that the genius that went into making his aircraft was not lost in vain. The period spanning World War II and the subsequent decade witnessed intensive aircraft development, featuring innovations like turbojet and rocket propulsion, flying wings, parasite fighters, reconnaissance planes, and 10-engine bombers. Many of these endeavours proved successful, but the XFY-1, known as the Flying Pancake, stood out as an abject failure. The Chance Vought division of the United Aircraft Corporation and its predecessor companies had previously supplied the US Navy and Marine Corps with successful aircraft, notably the F-4U Corsair, a highly capable carrier fighter that served in various air forces from 1942 well into the 1970s. Initiated in mid-1939, the F-5U program was spearheaded by senior designer Charles H. Zimmerman. Known for pioneering experimental designs, Zimmerman had a career with the National Advisory Committee for Aeronautics and later NASA. His concept for the XFY-1 focused on maintaining a uniform airflow over the entire wingspan, creating a flat, disc-shaped wing fuselage. This design, resembling a pancake, was believed to allow the aircraft to take off and land at exceptionally low speeds while maintaining desirable high-speed performance, a crucial quality for Navy fighter aircraft operating from carriers. Two piston engines buried in the body on each side of the cockpit power propellers at the leading edge of the pancake. This unusual configuration gave the promise of both high and low flight speeds, with high-angle attitudes for landing, takeoff, and other maneuvers. The wing fuselage of the XFY-1, resembling a flying pancake, featured a complex empennage that included two normal-looking horizontal stabilizers and elevators, two rudders, and two large elevators on the midpoint of the fuselage. In the development phase, Chance Vought constructed a quarter-scale aircraft named V-173 with a loaded weight of approximately 3,050 pounds, roughly one-fifth the weight of the full-size XFY-1. The V-173 made its first flight on the 23rd of November 1942, following extensive wind tunnel tests. Notably, aviation pioneer Charles A. Lindbergh and several Navy pilots piloted the V-173 during its 131 hours of successful flight tests, despite being underpowered. The V-173's unique tall undercarriage gave it a ground angle of 22.25 degrees, and the pilot entered the aircraft beneath the cockpit. This setup made forward visibility almost non-existent until the tail lifted from the runway. Transparent panels were incorporated between the pilot's feet to enhance downward visibility during landings. Remarkably, the V-173 could typically take off within 200 feet and even achieve vertical takeoff into a 25-knot wind. By mid-1942, work commenced on the enlarged VS-315, which would later become the Navy's XFY-1. In September 1942, the Navy expressed its intent to procure two of these aircraft. For the operational XFY-1, designer Zimmerman aimed for a phenomenal speed range of 40 to 425 miles per hour. With improved engines and water injection, he envisioned pushing the speed range to 40 to 460 miles per hour. The engine arrangement posed significant challenges for the Chance Vought team throughout the aircraft's development program. The propellers, which rotated in opposite directions, were attached to shafts enclosed by circular nacelles extending forward from the fuselage. In addition, because of the high angles of attack that the aircraft was intended to adopt for extended periods, careful attention had to be given to the design of the fuel and oil systems to ensure they would operate at all attitudes for indefinite periods. The XFY-1, generally similar in configuration to the V-173, was designed to sit at an angle of 18.75 degrees, a slightly less severe angle than the prototype but still notable. The oleo legs featured twin small diameter wheels, which folded upward and aft into the lower fuselage surface and closed by clamshell doors. For carrier operations, an arresting hook was to be fitted, a complex assembly that retracted and was enclosed by doors. As a combat aircraft, the XFY-1 was equipped with 3.50 caliber machine guns on each side of the cockpit, with a magazine capacity of 400 rounds per gun. Provisions were made to replace 4 of these guns with 4 20mm cannons. Additionally, the aircraft could carry 2 1,000-pound bombs under the fuselage. A wooden mock-up of the XFY-1 was ready for inspection by the Bureau of Aeronautics on the 7th of June 1943 in Stratford, Connecticut. After some revisions, it gained approval in August, though the 2-aircraft contract was not signed until the 15th of July 1944. The first aircraft was to be equipped with R2077 engines, rated at 1,350 horsepower for takeoff, while the second would have the XR2002 fitted with Wright turbo superchargers. The 16-foot diameter propellers were contra-rotating, turning outboard to prevent prop wash from disrupting the airflow over the wing fuselage. The first XFY-1 was rolled out of the assembly hall at Stratford in late June 1945. It began ground testing on the 20th of August, with flight testing envisioned to start a year later. The second XFY-1 will be used for static tests. The flight test schedule was delayed because of difficulty obtaining the articulated propellers, which were not available until 1947. The XFY-1 faced challenges beyond its configuration. Vibration problems and issues with the complex gearboxes added to the list of difficulties. The planned flight tests were set to take place at the Muroc Dry Lake in California. However, with the conclusion of World War II in August 1945, the US Navy underwent a thorough review of its aircraft development and procurement initiatives. The XFY-1 became an obvious target for cancellation. Apart from financial constraints in naval aviation, the Navy was actively sponsoring several fighter and attack aircraft with turboprop and turbojet engines. Consequently, the viability of a piston-engine combat aircraft for future roles was highly questionable. On the 17th of March 1947, the Navy officially cancelled the XFY-1 program and issued orders to scrap the 2 aircraft. This action was carried out in 1948. Unfortunately, the Flying Pancake never had the opportunity to take flight. The Miles Aircraft concern conceived the M39 Libellula during the early 1940s, amid the turmoil of World War II. Initially, the concept aimed to simplify landing aircraft on carrier decks, addressing visibility challenges caused by forward-mounted engines and large wing mainplanes. A novel tandem wing arrangement was pursued to mitigate risks, resulting in a series of concepts explored by Miles during the war. The overarching term for these Miles designs was Libellula, named after the taxonomic family of the Dragonfly. The groundwork for this project began with the M35, essentially a technology demonstrator for a single-seat naval fighter. Miles pursued this endeavour independently, using the tandem wing setup to reconfigure the centre of gravity found in conventionally configured military aircraft. In a brief span of 6 weeks, Miles engineers introduced the M35. This aircraft was equipped with a single de Havilland Gypsy Major air-cooled inline engine, boasting 130 horsepower. During testing, the engine exhibited temperamental behaviour and longitudinal control was problematic. Nevertheless, this design provided valuable insights into the unconventional arrangement, contributing to future developments in the field. Building on this knowledge, a new design emerged, scaled at 5/8 and designated as M39B. This single-seat demonstrator featured a pair of de Havilland Gypsy Major IC air-cooled inline engines, each with 130 horsepower, showcased in outboard nacelles beneath the rear wing mainplanes. The frontal mainplane was now positioned low against the sides of the cockpit, and the fuselage boasted a finely contoured shape from nose to tail. The undercarriage transitioned to a traditional tricycle configuration. Given the larger scope of the M39B project, its dimensions were appropriately increased. The wingspans now measured 25 feet at the front set and 37.5 feet at the rear. The overall length extended to 22.3 feet, and the maximum weight rose to 3,200 pounds. As constructed and tested, the M39B achieved speeds of up to 166 miles per hour thanks to its twin-engine setup and tandem wing approach. The maiden flight for the M39B occurred on July 22, 1943. A dorsal fin was later fitted at the fuselage aft for additional control to complete the M39B's iconic three-finned appearance. Up until September of 1943, all of the work on the two aircraft, M35 and M39B, was as a private venture. From then on, the British Air Ministry decided to offer a formal development contract to Miles. Shortly after, Miles sought interest from the United States Army Air Forces, aware of their consideration of the domestic Curtiss XP-55 Ascender, which shared a tandem wing pusher engine configuration and was intended as a fighter. The USAF's response revealed a general lack of interest in the Miles product, as the XP-55 itself faced issues, particularly with stalls and recovery. The American program only progressed to flight testing, producing 3 aircraft in total. The M39B underwent evaluation at the Royal Aircraft Establishment, encountering problems from the outset. A new undercarriage had to be installed, and several accidents necessitated constant repairs, keeping the aircraft grounded for extended periods. Despite its unconventional arrangement, overall handling characteristics were considered normal. While landing and takeoff required adjustments to the standard routine, these were deemed forgivable, and stalling and recovery performed as anticipated. In 1941, the RAF issued a new specification for a medium-class, medium to high-altitude, high-performance bomber. Miles responded with its M39 project, a modified version of the M39B featuring a pressurized cockpit for a crew of 3. The proposed power for the M39 project included either 2 Rolls-Royce Merlin 61 series inline engines or 3 Powerjets W2500 gas-powered turbine engines. This design featured a significant wingspan increase, measuring 37.5 feet at the frontal wing and 55.8 feet at the rear pairing. The overall length expanded to 35.9 feet, and the maximum weight surged to 26,750 pounds. The envisioned cruising speed was 360 miles per hour, and armament was planned to include 2 20mm cannons in the wing roots, 1 gun per root, along with an internal bomb bay in the fuselage, capable of carrying up to 6,000 pounds of bombs. Ultimately, the de Havilland DH-99 Vampire fulfilled the specified requirements. The Hawker P-1005 also competed for a period. Although a prototype M39 high-speed bomber was ordered under a November 1943 contract, it was never constructed. The RAF's bomber needs were met elsewhere, leading to the termination of the M39 project, along with the data-collecting M39B aircraft. While surviving the war, the M39B lasted only until 1948, when it was scrapped. Despite its shortcomings, the Miles Libellula left an indelible mark on aviation history. Its bold, unconventional design inspired future aircraft engineers to think outside the box and take risks. The Libellula remains a testament to the power of human ingenuity and the boundless potential of innovation. The Miles M39B Libellula serves as a fascinating case study of a daring, experimental aircraft that ultimately fell short of expectations. Its unique design, ambitious goals, and ultimate cancellation offer valuable lessons for future aviation endeavours. In the post-World War II era, the concept of military aircraft capable of vertical takeoff and landing, VTOL, captured the imagination of designers and military strategists globally. The increasing performance of land-based jet aircraft necessitated longer runways, which in turn presented vulnerabilities. A single conventional bomb on a runway could incapacitate an airbase and its aircraft. Naval aviation faced similar challenges, as aircraft carriers were susceptible to attacks. Despite the number of combat aircraft a carrier could operate, any damage to the vessel rendered its air power ineffective. The idea of VTOL-capable aircraft emerged as a potential solution to these issues. Such aircraft could be launched and recovered from small, temporary forward air bases or even from vessels considerably smaller than traditional aircraft carriers. Recognizing the strategic importance of VTOL capabilities, the USAF and US Navy jointly sponsored Project Hummingbird in 1947. This project aimed to explore and study the practical application of VTOL technology, laying the groundwork for innovative designs like the Convair XFY-1 Pogo that would follow. This project was able to use data captured from Nazi Germany at the end of World War II, and, in particular, design work on a projected German VTOL aircraft, the Focke-Wulf Triebflügeljäger. The Triebflügeljäger was a radical design concept created in 1944 in response to the increased Allied bombing of German industrial targets. Its design never went further than the creation of wind tunnel models, but the concept of a tail-sitter VTOL aircraft captured the interest of the US Navy. They were interested in a fighter that could be launched from any warship and even from transport ships or tankers. The prospect of equipping each US Navy ship with its own point defense interceptor led to a significant re-evaluation of the necessity for vulnerable aircraft carriers. Building on the findings of Project Hummingbird in 1948, the US Navy initiated a more detailed study and, in 1949, sought the expertise of the National Advisory Committee for Aeronautics to assess the feasibility of developing a tail-sitter VTOL interceptor. This concept, resembling the Triebflügeljäger in some aspects, employed a conventional fuselage with an engine driving contra-rotating propellers in the nose. A successful model demonstrated the ability to take off and land vertically, seamlessly transitioning to conventional forward flight. In May 1951, the US Navy awarded contracts to both Convair and Lockheed for the production of 2 prototypes, each of a VTOL tail-sitter fighter. Both the Convair and Lockheed aircraft were slated to be equipped with the powerful Allison T-40 engine, a development based on a pair of T-38 Allison turboprop engines arranged side by side, delivering power to a shared reduction gearbox. This marked a significant step forward in the pursuit of effective VTOL capabilities for naval interceptors. The power of the engine was estimated to be over 5,000 kilowatts. In comparison, the Pratt & Whitney radial engine fitted to the Vought F4U-4 Corsair, then in service with the US Navy, provided around 1,700 kilowatts. The pilot's seat was able to rotate through 45 degrees to allow it to be used comfortably in both vertical and horizontal flight. No armament was ever fitted to the XFY-1, but this was expected to take the form of either 4 20mm cannon fitted in the wing's outboard of the massive propellers, or a pack containing 48 folding fin unguided aerial rockets. The first XFY-1 prototype reached completion in early 1954 and underwent testing in a fixed vertical stand at Lindbergh Field in San Diego. The performance in this setting was satisfactory, prompting the decision to proceed with the next phase of development, involving tethered and untethered flight testing. The second prototype was transported to NAS Moffett Field near Sunnyvale, California, where a specially designed tethered test rig was set up in the colossal Hangar No. 1. This historic hangar, originally constructed in the 1930s, once housed the US Navy airship USS Macron. The rig featured a motorized reel attached by cable to the XFY-1 propeller hub, providing a means for emergency reeling to swiftly return the aircraft to an upright position. The challenging task of determining whether the XFY-1 could actually fly fell to Lieutenant Colonel James F. Skeets Coleman, a US Marine Corps Reserve pilot and engineering test pilot for Convair. Tethered flights were conducted with assistance from Convair flight test engineer Bob McGreary, who controlled the tether mechanism, ready to pull the XFY-1 upright in case Coleman lost control. Coleman faced the daunting responsibility of testing an aircraft that was both radically different and potentially hazardous, making his role as a test pilot exceptionally challenging. In November 1954, Lieutenant Colonel James F. Skeets Coleman achieved a significant milestone by executing the first transition to horizontal flight in the XFY-1. Remaining in conventional forward flight for over 20 minutes, he safely returned the aircraft for landing. The XFY-1, powered by significant thrust in a compact and streamlined airframe, proved to be remarkably fast. Even with throttles at their minimum setting, the aircraft cruised at speeds exceeding 300 miles per hour. During level flight, it often surpassed the conventional chase aircraft assigned to monitor its progress. The absence of speed brakes or spoilers made landing at these high speeds particularly challenging. To address this, Coleman developed a unique landing technique. Approaching the landing field at around 300 miles per hour, he would pull the stick all the way back when close to the landing point, causing the XFY-1 to enter a vertical climb. As the speed decreased, he carefully added power until the aircraft reached a hover at an altitude of around 1,000 feet. Then, while looking over his shoulder at the ground, he gently reduced power during the descent. The XFY-1's lack of stability in the hover demanded constant control corrections during descent, especially as it encountered turbulence from its own reflected prop wash near the ground. One of the most demanding aspects of landing involved judging the aircraft's rate of descent within safe limits, a task requiring the pilot's attention to the ground over his shoulder and continuous control input to maintain stability. The unique characteristics of the XFY-1 demanded exceptional skill and precision from its pilot during the landing phase. As an aid, Convair mounted a small radar altimeter pod on the left wingtip. This was connected to 3 lights in the cockpit. Green meant that the aircraft was in a stable hover, amber meant that it was descending within safe limits, and red meant that the rate of descent was too fast. Even with this device fitted, the XFY-1 was a fiendishly difficult aircraft to land. Coleman was clearly an exceptional pilot, and when another US Navy pilot was allowed to fly the XFY-1 for the first time in May 1955, he was lucky to survive the experience. The XFY-1 never took to the skies again, and the project officially concluded in August 1956. Lockheed's XFV-1 tailsitter II was abandoned without achieving vertical takeoff or landing. From a strictly technical standpoint, the XFY-1 demonstrated success. It executed numerous flights, showcasing its ability to fly conventionally and to perform vertical takeoffs and landings. In this limited sense, it marked the first successful military VTOL aircraft. However, as a potential operational aircraft, the XFY-1 faced insurmountable challenges. Landing safely was an exceedingly difficult task. Lacking automated flight stabilization in the hover, it demanded constant corrections from the pilot, who also had to closely and continuously monitor descent rate, position, and attitude. The second critical issue leading to the project's cancellation was performance. By the mid-1950s, jet interceptors capable of exceeding Mach 1 were being produced. In just a few years, operational aircraft would achieve Mach 2 capabilities. Despite the formidable power of its turboprop engine, the XFY-1 could never reach even Mach 1. This limitation placed it at a distinct and insurmountable disadvantage as a combat aircraft, making its operational viability untenable in the face of evolving technological standards. Conceived during the latter part of World War II, the Miles M57 Aerovan aimed to serve as an economical aircraft for transporting passengers and cargo over short distances, capable of landing and taking off from rugged airstrips. Development of the Aerovan began in early 1944, with the vision of creating a cost-effective, low-powered freighter suitable for both civilian and military applications. George Miles, throughout the Second World War, championed the adoption of such an aircraft in the British military, challenging the prevailing reliance on gliders. After completing the development of the Miles Messenger, Miles's design team recognized the potential of a more powerful and heavier aircraft, approximately double in capacity. This envisioned aircraft could serve as a robust military transport, particularly for operations like the Burma campaign against Imperial Japan and specialized roles such as air ambulance missions. Anticipating post-war demand from civilian operators, Miles foresaw the Aerovan's popularity in the civilian market. However, the War Ministry held a different perspective, delaying the project until the conclusion of hostilities and the Victory in Europe Day celebrations on May 8, 1945. The prototype aircraft was built at the Miles factory in Berkshire, debuting on January 26, 1945. The plane featured a high wing design, a high tail, and large rear clamshell doors. Miles decided that a pair of Blackburn Cirrus major piston engines would power the British-built plane. After its maiden flight, test pilot Tommy Rose gave it rave reviews for its performance. The aircraft was also capable of lifting heavy payloads, something Miles thought the Air Ministry would like. Constructed from plastic-bonded plywood with elements of spruce and metal, the Miles Aerovan was a twin-engined high-wing monoplane. Its design featured a fixed tricycle undercarriage and 3 vertical tail and rudder units, resembling the Miles Messenger in its overall configuration. The wing boasted electrically actuated flaps, a recent innovation allowing adjustment to any angle. Ground steering options included both differential braking and differential operation of the throttles. The Aerovan's forward fuselage had a relatively deep-sided structure, requiring a substantial fin area. The cockpit, situated beneath a large clear perspex canopy, accommodated 2 pilots, while circular windows on either side of the pod-shaped fuselage provided views for passengers. Access to the cabin and cockpit was granted through a starboard side door, with additional amenities like soundproofing often included for enhanced comfort. Known for its lifting prowess, the Aerovan could carry payloads of up to 1 ton, with enough space to accommodate a typical family car, loaded through rear-set clamshell doors. The standard Aerovan was powered by a pair of Blackburn Cirrus major piston engines. Alternative power plants included the de Havilland Gypsy Major and the Lycoming 0435, often necessitating the use of enlarged fins and rudders to cope with the increased power under all circumstances. By swapping the engines, the maximum speed could be increased by up to 20 miles per hour and the rate of climb by up to 50%. Work on the Aerovan was resumed shortly after Victory in Europe Day. While there was immediate demand for the type amongst civilian customers, Miles were not able to keep up with the rate of orders incoming, an outcome which aviation author Don Brown attributed to the Air Ministry's decision to place the project on hold. Diverging from the prototype, the production model of the Aerovan underwent notable changes, including an 18-inch elongation of the fuselage and the adoption of porthole windows in place of rectangular ones. In 1946, full-scale production of the Aerovan commenced, with the majority sold to civilian operators globally. While predominantly a civilian aircraft, some military interest emerged, with Israel and New Zealand among the notable customers. Despite having a license for Aerovan production in France, no such aircraft were ever manufactured in the country. In New Zealand, a single Royal New Zealand Air Force aircraft was adapted for aerial fertilizer spreading, and another for aeromagnetic survey work, though the latter proved unsuccessful. In 1957, a Mark IV model underwent research, with the Hurrell Du Bois high aspect ratio wing becoming known as the Miles HDM 105. Production abruptly halted in late 1947 due to Miles's bankruptcy and subsequent dissolution. During the Cold War, the US Army was actively exploring various aviation technologies to gain an edge over the expanding threat posed by the Soviet Union. The VZ-4DA, also known as the Model 16, developed at Fort Eustis, was one such result of this era. Edmund R. Doak, the president of Doak Aircraft Company in Torrance, California, had been experimenting with ducted fans and related air-moving concepts since 1935. He proposed a vertical takeoff and landing VTOL aircraft to the US military as early as 1950. Doak successfully convinced the Army Transportation Research and Engineering Command at Fort Eustis that his VTOL aircraft could amalgamate the benefits of a conventional fixed-wing fighter with the helicopter's capacity to take off and land in confined spaces. Recognizing the potential vulnerability of Allied airbases and runways to Soviet first strikes, the Army considered the ability to take off and land in small areas crucial. VTOLs, similar to helicopters, offer the advantage of lingering longer over a target, hovering, and even flying backwards. In essence, the Doak Model 16 appeared to be an ideal utility and observation platform, with the potential to deliver fire to ground targets. On April 10, 1956, the Army awarded Doak a contract for a single research vehicle, initiating the development of the experimental VTOL aircraft. Only one prototype, serial number 569642, would ever be built and tested. The Doak 16's two 5-foot diameter ducted fiberglass fans were located on its wingtips. Positioned vertically for takeoff and landing, they were rotated into a horizontal attitude for normal forward flight, the first time this concept was successfully employed. A rotation speed of 4,800 RPM was required to achieve lift. To maintain a low weight, the fuselage of the Doak 16 was constructed using uncovered welded steel tubing, later covered with molded fiberglass at the nose and thin aluminum sheeting on the aft fuselage. This modification was made when it was discovered that the open frame was hindering forward speed trials. The wings and tail, on the other hand, were made of metal. Edmund R. Doak demonstrated resourcefulness in cost-cutting measures, incorporating the landing gear from a Cessna 182, seats from a North American F-51, and duct actuators from Lockheed T-33 electric flap motors. The two-place tandem cockpit could accommodate a pilot and observer, with standard stick and rudder controls for the pilot. The aircraft's empty weight was 2,400 pounds, and its gross weight was 3,300 pounds. It had a wingspan of 25 feet 7 inches, measured 32 feet in length, and stood 10 feet 1 inch high. By 1958, the Doak 16 had undergone multiple test flights at Torrance Municipal Airport. Its first hovering flight took place on February 25, 1958, and on May 5, 1959, the prototype achieved its first conversion from vertical to horizontal flight, and vice versa. The Doak 16 completed 50 hours of flight testing, including 32 hours on a test stand, 18 hours of tethered hovering, and taxiing. Throughout this process, some undesirable flight characteristics emerged, such as the aircraft's tendency to nose up during the transition from hovering to forward flight, and a short takeoff and landing performance that fell below expectations. But engineers believed these problems were all solvable. Transferred to Edwards Air Force Base in October 1958, the Doak 16 underwent another 50 hours of testing, in the course of which it logged some promising performances. The VTOL single 825 horsepower Lycoming T53L1 turbine power plant gave it a maximum speed of 230 miles per hour, a cruising speed of 175 miles per hour, and range of 250 miles. A T-box on the engine transmitted power to the ducted fans through a 4-inch tubular aluminum shaft and two smaller steel shafts. The aircraft's service ceiling was 12,000 feet, and it had a flight endurance of 1 hour. These performance attributes led to its acceptance by the Army in September 1959. Officially designated the VZ-4DA, the prototype was then transferred to NASA Langley Research Center in Hampton, Virginia for further testing. In late 1960, a recession in the aerospace industry prompted Edmund Doak to lay off 90% of his employees. During this period, Douglas Aircraft took over the VZ-4DA project by purchasing the patent rights and engineering files. 4 Doak engineers were also hired by Douglas to continue their work at El Segundo. They implemented a larger engine and made structural improvements. However, after 3 more years of testing, the Army withdrew the VZ-4DA from active trials. NASA subsequently acquired it in 1973, and it was later transferred to Fort Eustis, where it remained in storage for a time. The demise of the VZ-4DA as a viable Army aircraft can be attributed to the evolving preferences within the Army. As the helicopter emerged as the Army's preferred mode of transport during the Doak 16's development, the focus shifted to funding rotorcraft, leading to a reduced emphasis on unconventional prototypes, including the VZ-40A, which were previously under consideration for production. The changing strategic priorities within the Army contributed to the discontinuation of the VZ-40A as an active military aircraft. In the early years of the Cold War, with military airfields deemed vulnerable to Soviet missile attacks, the concept of underground airports gained traction among Western governments. The rationale was that subterranean bases would offer better protection against enemy assaults and could potentially serve as hangars and launch sites for future stealth aircraft. However, the development of underground airports required the simultaneous creation of high-speed aircraft with vertical takeoff and landing VTOL capabilities, as traditional jets rely on runways and open skies for takeoff. One early attempt to build such an aircraft was made by the Canadians. The Avrocar emerged from a series of blue sky research projects led by designer Jack Frost, who joined Avro Canada in June 1947 after gaining experience with several British firms. At the time, Frost was particularly focused on jet engine design, seeking ways to enhance the efficiency of the compressor without complicating the simplicity of the turbine engine. During the 1950s, Jack Frost initiated the ambitious Project Y, with the aim of developing a vertical takeoff and landing aircraft capitalizing on his newly designed high-power engine. This project represented a forward-looking exploration into VTOL capabilities, aligning with the broader interest in unconventional aircraft designs during the Cold War era. The innovative design featured the redirection of thrust through ducts along a distinctive delta wing, reminiscent of a spade on a playing card. Despite encountering financial constraints and skepticism from the military, Frost persevered in his experimentation. He explored the Quanda effect to enhance the VTOL capabilities, seeking a more practical solution for the project. Although Project Y secured funding from the Canadian Defence Research Board and the US, the Avrocar, a project initiated by designer Jack Frost at Avro Canada, faced eventual cancellation due to safety issues encountered during testing. The concept of the aircraft went beyond conventional boundaries, aiming to create a supersonic large-disc fighter with the unique capability of performing vertical takeoffs and landings. The project reflected the era's challenges and aspirations in pushing the limits of aeronautical innovation. To gather flight data on the basic concept while engine development continued, Frost proposed the construction of a smaller proof-of-concept test vehicle in 1958, which he named the Avrocar. Simultaneously, the US Army was engaged in various experiments involving smaller vertical takeoff and landing aircraft, envisioning them as flying jeeps. The Army became interested in Avro's concept, and Frost pitched the smaller design as a prototype suitable for the Army's needs and an aerodynamic testbed for the WS-606 engine. Initial performance requirements for the Avrocar included a 10-minute hover capability in ground effect and a 25-mile range with a 1,000-pound payload. Avro secured a $2 million joint services contract for the construction and testing of 2 Avrocars, designated by the Army as VZ-9AV. The Army expressed significant interest in the Avrocar program, considering it a potential replacement for helicopters. However, safety concerns during testing eventually led to the cancellation of the project, highlighting the difficulties in realizing unconventional and ambitious aircraft concepts during that period. Additional Air Force funding, approximately $700,000, was allocated to the project from the 606A program. In March 1959, a $1.77 million contract was secured for a second prototype. Despite setbacks, including the cancellation of the Avro CF-105 Arrow program in 1959, the Special Projects Group at Avro Canada continued its work on the Avrocar, with renewed involvement from company leadership. The USAF Project Office initially recommended cancelling the WS-606A and related work, but an extensive effort led by Jack Frost resulted in the authorization to continue the Flying Saucer programs in May 1959. The Avrocar, notable for its disc-shaped design reminiscent of a frisbee, featured an 18-foot diameter and a thickness of 3.5 feet. Supported by a robust equilateral triangle truss, its distinctive element was the 124-blade turbo rotor, centrally positioned and powered by 3 Continental J69 T9 jet engines. The airframe, predominantly constructed from aluminum, had an empty weight of 3,000 pounds. The initial undercarriage included 3 small cast-steering wheels, later replaced by skids during testing. Piloting the Avrocar involved a single side-mounted control stick, enabling conventional pitch, roll and yaw control through adjustments in airflow. The attitude thrust control system, positioned outside the main disc, facilitated changes in vertical lift and directional control. To counteract inherent instability during forward flight, a mechanical stability augmentation system was implemented. The Avrocar's unique design and control mechanisms aim to address the challenges of achieving vertical takeoffs and landings while ensuring stability during different flight phases. Leveraging the turbo rotor's significant angular momentum, it functioned as a powerful gyroscope, stabilizing the craft. The crew compartment accommodated 2 individuals in separate cockpits integrated into the airframe. Practical testing initially involved a single pilot, with occasional flights featuring an observer in the secondary cockpit. Addressing control intricacies, Avro test pilots honed a nuanced understanding of the craft's sensitive inputs. Chief Development Test Pilot Petocci achieved a hands-off flight after resolving control issues, marking a notable advancement. However, despite progress, Avro test pilot Peter Cope, USAF project pilot Walter J. Hodgson, and NASA's Ames Research Center chief test pilot Fred J. Drinkwater III all emphasized the persistently challenging nature of the Avrocar. Drinkwater likened flying it to balancing on a beach ball. The first Avrocar, 587055, faced hover issues due to exhaust mixing and limited lift, leading to modifications. The second, 594975, encountered uncontrollable roll and pitch oscillations during tethered hover attempts, attributed to the hubcapping effect, prompting numerous modifications. Despite improvements, nozzle control issues and stability problems persisted. A new design with separate hover and forward flight controls in 1960 demonstrated better control but maintained pitch instability. Further modifications in 1961 improved hover control, allowing speeds up to 100 knots, but pitch instability persisted. A second evaluation in June 1961 revealed control problems and limited flight above critical altitudes. Before modifications could be implemented, funding ran out in March 1961. Despite Frost's proposals for a modified design, the Avrocar and related WS-606A supersonic VTOL programs were officially cancelled in December 1961 by the US military. The VZ-9AV Avrocar and its nascent VTOL technology are credited with paving the way for the development of subsequent VTOL-capable aircraft, such as the AV-8B Harrier II, V-22 Osprey, F-22 Raptor, and others currently employed in various missions by the US military. Despite its challenges, the Avrocar played a significant role in advancing vertical takeoff and landing technology, contributing to the evolution of modern VTOL aircraft. The Ryan XFY-1 Vertifan was an experimental jet-powered VTOL vertical short takeoff and landing aircraft developed in the 1960s. The United States Army commissioned the Ryan VZ-11RY in 1961, later redesignated as the XV-5A in 1962. This initiative was part of the Army's exploration of VTOL capabilities, alongside the Lockheed VZ-10 Hummingbird, which was later redesignated as the XV-4 in 1962. The XV-5 was equipped with 2 General Electric J85 GE5 turbojets, each providing 2,658 pounds of thrust. Vertical takeoff and landing VTOL capabilities were achieved through the use of General Electric X3535 lift fans integrated into the wings and a smaller fan in the nose. These lift fans were powered by engine exhaust gas. Each wing featured a 62.5-inch diameter lift fan with a hinged cover on the upper wing surface, which could be opened for VTOL operations. The 36-inch nose fan played a role in pitch control but posed challenges in terms of handling characteristics. The lift fans collectively generated vertical lift of approximately 16,000 pounds, which was nearly 3 times the thrust produced by the turbojets. Yaw control was facilitated by a set of louvered vanes beneath each wing fan, enabling the vectoring of thrust fore and aft. The XV-5 Vertifan was a part of the Army's exploration of innovative VTOL technologies during the 1960s, showcasing unique lift fan configurations for vertical takeoff and landing. The engine power setting determined the lift from the fans, as fan RPM was determined by the exhaust output from the J85 engines and the load on the fan. Roll control was by differential actuation of the wing fan exit louvers. Aircraft performance was subsonic, with delta wings superficially similar to those on the Douglas A4 Skyhawk. The Vertifan had an unusual intake position above the 2-seat side-by-side seating cockpit and a T-tail. The XV-5A was painted in army green, while the XV-5B had a white NASA color scheme. Despite its unique design, the lift fans on the XV-5 didn't generate the anticipated thrust, and the transition between vertical and horizontal flight proved to be challenging and abrupt. This aircraft marked one of the last crewed endeavours by Ryan, a company that shifted its focus to drone manufacturing in the mid-1960s. The XV-5 was part of a diverse array of attempts to create successful vertical takeoff aircraft. However, the lift fan system used in the XV-5 was heavy and occupied a considerable internal volume. Only the Hawker Siddeley Harrier remained operational by the turn of the 21st century, along with technology enabling the use of a shaft-driven fan in the Lockheed Martin F-35B. The combination of the J85 engine and lift fan in the XV-5 was a precursor to developments that led to the first high bypass ratio engine by General Electric, the TF-39. The lift fans were driven by turbine blades mounted around the fan's periphery, with a mass flow 13 times greater than that of the gas generator and resulting in a 3-fold increase in thrust compared to a propelling nozzle. Following the demonstration that large volumes of air could be moved through a lift fan, an 80-inch tip drive fan, turned through 90 degrees and powered by a more potent J79 engine, was constructed to showcase an efficient cruise fan. This concept of a large diameter cruise fan was incorporated into the General Electric TF-39 engine utilized on the Lockheed CF-5 Galaxy. The XV-5, while not achieving widespread success, played a role in advancing lift fan technology and contributing to subsequent developments in aircraft propulsion. 2 12,500-pound XV-5As were evaluated in late 1966 by 15 test pilots. One was destroyed in a crash during a public flight demonstration on the 27th of April 1965, killing Ryan test pilot Lou Everett. As a result of this accident, the conversion switch was changed to a lift-lock toggle and relocated on the main instrument panel ahead of the collective lever control. The XV-5 presented challenges during landing due to various factors. Yaw control relied on altering the angle of the lift fans in opposing directions, but this method proved insufficient for precise low-speed handling. The duct doors further complicated control, causing significant pitch changes even at low speeds. Additionally, the aircraft experienced poor acceleration during standard runway takeoffs. Promotional materials and tests explored the potential of a rescue version equipped with a winch to hoist individuals into a compartment behind the pilots. However, a tragic incident occurred on October 5, 1966, during trials for the rescue aircraft. The second XV-5 sustained extensive damage when a suspended horse collar survivor sling was drawn into a wing fan. Despite the fan still functioning well enough for controlled flight, Major David H. Tittle, the pilot, suffered fatal injuries due to the ejection seat propelling him out of the aircraft after it hit the concrete airport surface. Following the accident, the second aircraft was reconstructed as the modified XV-5B and testing continued until 1971. An XV-5B is currently on display at the United States Army Aviation Museum in Fort Novosel, Alabama. Despite the cancellation of the program, the ducted fan concept was deemed successful, leading to several proposed follow-up programs. The ducted fans were recognized for their quiet operation, especially for the era, and their ability to operate from standard surface materials without causing damage. This set them apart from other VTOL aircraft, which often require protective mats to prevent ground surface damage from their exhaust, a concern mitigated by the cooler exhaust from ducted fans. Throughout the history of military transport aviation, developers of new projects have consistently aimed to enhance aircraft and helicopter capabilities, including increasing carrying capacity, speed, and range of flight. However, there's also been interest in light or ultralight vehicles, capable of aerial transportation for small loads or passengers, catering to specific needs. Over different periods, numerous projects in this category have emerged. For instance, one of the early endeavours to create a flying jeep for military applications was the development of the XV-8 Fleep by the American company Ryan. In response to the diverse transportation needs of the military, including the requirement for aircraft capable of transporting light loads or small groups of personnel, Ryan Aeronautical Company initiated work on its version of such an aircraft in the late 1950s. This project incorporated several innovative ideas aimed at reducing the weight and size of the structure while meeting the necessary flight and carrying capacity requirements. Designated as the XV-8, the aircraft project was informally dubbed Fleep, or Flying Jeep. However, official military documents refer to it as the FWAUV, Flexible Wing Aerial Utility Vehicle, in other words, auxiliary air transport with a flexible wing. Notably, the official designation mirrored the aircraft's goals and fundamental design features, while the informal name encapsulated its operational essence. To achieve the desired characteristics, the prospective aircraft needed to minimize weight. A solution proposed was to utilize a flexible wing, commonly known as a wing rogolo, to reduce the structure's mass. Back in 1948, Francis and Gertrude Rogolo proposed an original wing design suitable for use in light aircraft. It was originally proposed to use a frame of 3 parts of great length, to which it was necessary to fix a square or diamond-shaped canvas. In the future, a new design of such a wing appeared, featuring a different composition of the power elements and the triangular shape of the canvas. The transition from traditional rigid wings to the Rogolo system in the Ryan XV-8 project was notable for its simplicity and cost-effectiveness in production. One characteristic feature of this aircraft was its ability to control flight by adjusting the relative position of the wing and the aircraft's centre of gravity. However, the flexible wing also had its limitations, particularly in adverse weather conditions, which could restrict its operation in certain environments. Nevertheless, the Rogolo wing later found application in hang gliders. In the XV-8 project, the Rogolo wing was proposed for use, along with several other components serving various purposes. The unique characteristics of the wing, along with existing requirements and new ideas, contributed to the development of a complex aircraft structure capable of transporting people or cargo despite its simplicity. The fuselage of the XV-8 aircraft featured a straightforward design with essential components. A rectangular platform served as the basis, equipped with fixtures for cargo installation. Positioned in front of the platform was a small protruding unit housing the controls and pilot's seat within a nose cone. At the rear of the platform, a frame was provided for mounting the engine. Supporting structures, both in front and behind the platform, were attached to accommodate the unusual design of the wing, with additional components for wing control integrated into these structures. Ryan Aeronautical developed its own version of the flexible wing for use in the XV-8 project, contributing to the aircraft's unique design and capabilities. As a basis for this product, 3 metal pipes with a length of 26 feet, about 8 meters, were used. In the nose of the wing, 3 tubes were pivotally connected, which allowed them to move in the same plane. A special mechanism was used to change the relative position of the pipes of the wing frame, which implies the simultaneous movement of the side parts. Near the central part of the wing was placed a set of rigid beams, with the help of which the side pipes could be reduced to the central or conversely diluted to the sides. At maximum extension, the wingspan of the XV-8 exceeded 10 meters, while when folded it measured 3 meters. To manage the excessive spreading of the tubes, a control mechanism and several braces were employed. The wing structure comprised 3 pipe beams supporting a quadrangular canvas, forming the wing plane and generating lift. Upon extension, the side pipes created the characteristic wing profile with 2 curved sections at the rear. The leading edge exhibited a sweep of 50 degrees, and the total area, excluding canvas bends, measured 450 square meters. Various materials, including synthetic textiles and films, were tested for the canvas surface. Mounted on the central beam of the Rogallo folding wing were attachments for fuselage truss installation. This pipe was firmly affixed to a swinging arm hinged at the apex of the framework. The front arm of the rocker was linked to a system of rigid rods leading to the control post. Using the appropriate lever, the pilot could adjust the wing's angle of attack to suit the current flight conditions. Located at the rear of the fuselage was an engine mounting frame. The power plant employed was the Continental IO360A piston aircraft engine, delivering 210 horsepower, paired with a 2-bladed propeller with a diameter of 2.14 meters. During testing phases, the XV-8 Fleep underwent trials with and without engine covers for varying aerodynamic conditions. A substantial fuel tank, contributing to the vehicle's bulkiness, was situated in the central portion of the wing truss. To enhance aerodynamics, a vertical tail was integrated into the design. Mounted on a lightweight beam extending from the engine frame to the fuselage platform, a trapezoidal keel was attached, with its upper section pivotally connected to the central beam of the keel. The beam was designed so that when the angle of attack of the wing changes, the keel remains upright. There were drives to rotate the keel around the vertical axis, which it was proposed to use to control the course. For the transport of goods or passengers in the Project Fleep FWA-UV, it was proposed to use the platform in the central part of the fuselage, in close proximity to the center of gravity. The length of the cargo platform reached 2 meters, the width was slightly less at 1.5 meters. The Ryan XV-8 Fleep project aimed at maximizing the reduction in size and weight of the aircraft design, and it appears this objective was successfully achieved. The dimensions of the vehicle were kept compact, with a length not exceeding 8 meters, a wingspan of 10 meters when deployed, and a parking height of 4.4 meters. Folding the wing allowed for a reduction in the overall width of the aircraft to about 3 meters while maintaining other dimensions. The aircraft's own weight was a mere 506 kilograms, 1,115 pounds, emphasizing its lightweight construction. For flight preparation, it was suggested to load 68 kilograms, 150 pounds of fuel into the 6.8 kilogram, 15-pound tanks. With fuel and the pilot accounted for, the minimum flight weight of the flying Jeep was estimated at 658 kilograms, 1,450 pounds. This left a payload capacity of 385 kilograms, 850 pounds, resulting in a maximum takeoff weight of 1,043 kilograms, 2,300 pounds. To facilitate takeoff and landing, the aircraft was equipped with a simple non-removable landing gear. The cargo area between the wing trusses could accommodate standard ammunition boxes or weapons, and there was also space for several soldiers with their gear. The landing gear featured light trusses with vertical uprights at the corners of the cargo area, each fitted with a wheel, with telescopic shock absorbers based on springs. In 1961, the development company constructed a full-size model of the XV-8 Fleep aircraft and subjected it to wind tunnel testing, during which no significant issues were encountered. This suggests a promising outlook for the project's development and potential deployment. The proposed appearance of the machine allowed to fly, and the combined control of changing the position of the wing and keel could give the desired maneuverability. According to the results of the tests in the wind tunnel, it was recommended to continue the work and begin a full test on the airfield. For use in testing, the first prototype was built with the serial number 6313003. It was built on the original project and fully consistent with the above description. The initial prototype of the Fleep, distinguished by its characteristic appearance, underwent successful runway runs without any issues. However, challenges emerged during attempts to lift the flying Jeep into the air, highlighting both its strengths and weaknesses. To achieve takeoff and landing, a runway length of 170 meters was required, demonstrating the effectiveness of the wing's optimal angle of attack. However, this design feature proved to be a drawback in other flight modes, as swinging the wing and adjusting its angle of attack didn't provide the necessary control. The lack of adequate control in flight could potentially lead to serious consequences, particularly considering the intended military application of the equipment. Consequently, the XV-8 project required significant improvements to address these shortcomings. Further analysis identified necessary enhancements, including simplifying the wing's angle of attack control system to allow fixation of the central tube in one of two positions. Additionally, the updated design necessitated the incorporation of a complete tail with a set of control surfaces to improve maneuverability. The revised project aimed to meet these new requirements while preserving the compactness and lightweight characteristics of the aircraft's structure. Consequently, a second prototype, identified by the factory number 6313004, was promptly constructed according to the updated specifications. In accordance with the updated requirements, the second machine Fleep FWA-UV received a new version of the power elements of the wing. The three pipes were now connected by a transverse truss consisting of several separate elements. Instead of a complex structure mounted on the fuselage, a set of racks of a simplified design was used. At the same time, the hinge was kept to change the angle of attack of the wing. It was decided to streamline the design of the aircraft further by replacing the four-point chassis with a more simplified configuration, opting for a single central location for the front struts. Additionally, the traditional keel was eliminated, making room for more sophisticated components. The revised tail configuration featured two inclined planes, forming a V-shaped tail on the elongated tail section of the fuselage platform. These planes housed fixed components as well as pivotally mounted parts that could function as rudders. By synchronously or differentially deflecting these rudders, control over roll or yaw could be achieved. Another controlled surface, acting as the elevator, was positioned on the rear edge of the fuselage platform. In the updated Ryan XV-8 Fleet project, it was proposed to utilize changes in the wing's angle of attack solely during takeoff and landing. During horizontal flight, the wing would remain fixed in the appropriate position, with control primarily relying on the tail rudders. Prototype number 6313004 underwent testing, affirming the effectiveness of the modifications implemented. The handling significantly improved, reducing the risk of accidents. This advancement allowed for comprehensive flight tests to establish the machine's characteristics. The second prototype demonstrated a maximum flight speed of 96 km an hour, with a cruising speed slightly below 90 km an hour and a flight range of 193 km. With successful test results, the project's future prospects were determined, indicating promising potential for further development. A characteristic feature of the first version of the Project XV-8 FWA-UV was the maximum possible simplicity of the design, which allowed good weight returns to be achieved. Noticeable refinements of the device necessary to increase manageability and reduce the likelihood of an accident led to some increase in its own weight and a corresponding decrease in other parameters. In conclusion, despite its initial promise, the Ryan XV-8 Fleet project didn't meet the expectations of the potential military customer due to shortcomings in controllability and performance. The first version lacked adequate controllability despite its advantages in size and cargo capacity, while the second version sacrificed certain parameters in favor of improved controllability. Recognizing the limitations of the existing design, further development of the XV-8 project was deemed impractical, leading to its closure. However, the flexible wing used in the project showed great promise and potential for various applications. Despite its simplicity, the Rogerlo wing design proved to be of significant interest and paved the way for advancements in ultralight aviation. Although the XV-8 project didn't achieve tangible results in military re-equipment, it played a crucial role in advancing the understanding and development of flexible wing technology, contributing to future innovations in aviation. Built for the Air Force by Martin, the X-24A was a bulbous-shaped aircraft with 3 vertical fins at the rear for directional control. The X-24A boasted a weight of 6,270 pounds without propellants, with dimensions measuring just over 24 feet in length and nearly 14 feet in width. On April 17, 1969, Air Force Major Gerald Gentry piloted the X-24A for its inaugural unpowered glide flight. Gentry also commanded the vehicle during its first powered flight on March 19, 1970. Over the course of its operational lifespan, the X-24A undertook 28 flights, contributing to the validation of the concept that a wingless vehicle could execute unpowered landings akin to the HL-10 program. Decades later, in a cost-saving measure, the X-38 program managers opted to utilize the X-24A design, leveraging its complete aerodynamic database to minimize the need for additional wind tunnel tests that would have been necessary for a completely new design. The X-24A recorded its fastest speed of 1,036 miles per hour, Mach 1.6, with its highest altitude reaching 71,400 feet. Both of these milestones were achieved by NASA research pilot John Mank, who also piloted the craft on its final flight on June 4, 1971. The X-24B's design evolved from a family of potential re-entry shapes proposed by the Air Force Flight Dynamics Laboratory, each with higher lift-to-drag ratios. To reduce the construction costs of a research vehicle, the Air Force opted to return the X-24A to Martin for modifications. These alterations transformed its bulbous shape into a configuration resembling a flying flatiron, featuring a rounded top, flat bottom, and a double delta planform culminating in a pointed nose. John Mank took the helm for the maiden flight of the modified X-24B, piloting its first glide flight on August 1, 1973. He also commanded the vehicle during its inaugural powered mission on November 15, 1973. Notably, among the X-24B's final flights were 2 meticulously executed landings on the main concrete runway at Edwards, showcasing the operational feasibility of precise unpowered re-entry vehicle landings. These pivotal missions, executed by Mank and Air Force Major Mike Love, played a crucial role in shaping the flight procedures for modern space shuttle landings. The X-24B's last powered flight was on September 23, 1975, with Bill Danner at the controls, marking the conclusion of rocket-powered lifting body flights at the Flight Research Center. Interestingly, Danner also piloted the final X-15 rocket plane mission approximately 7 years prior. The X-24B achieved a top speed of 1,164 miles per hour, Mach 1.75, during a flight piloted by Love on October 25, 1974. Its highest altitude reached was 74,100 feet, accomplished by Mank on May 22, 1975. Today, the X-24B stands proudly on public display at the Air Force Museum located at Wright-Patterson Air Force Base in Ohio, serving as a tangible testament to its significant contributions to aerospace research and development. Over the years, scientists and designers across various nations have devoted efforts towards crafting aircraft with the most minimal takeoff and landing requirements. This approach aimed to reduce the demand for expansive landing sites, thereby enhancing operational versatility. However, achieving such benefits posed significant challenges, prompting aircraft manufacturers to seek unconventional technical solutions. Among the pioneering aircraft to successfully demonstrate shortened takeoff and landing capabilities was the Ryan VZ-3 Vertiplane. In the 1950s, American company Ryan Aeronautical embarked on the development of innovative aviation technologies aimed at improving these crucial flight characteristics. Leveraging a combination of established and novel technical solutions, the company aimed to produce an experimental aircraft meeting the desired specifications. The underlying technologies of this pilot project held promise for potential application in the creation of practical aircraft in the future. First of all, such a technique could interest the Army. To reduce the takeoff distance or to ensure vertical ascent into the air, different methods and designs of the aircraft can be used. In their new project, the designers at Ryan decided to apply the technology of deflecting the airflow. The wing of the aircraft of the new model was to be equipped with developed flaps of a large size that could have a significant impact on the movement of air, changing its direction and creating additional thrust. To test the original proposal in practice needed the help of a specialized experimental aircraft. The new project was assigned the working corporate designation Ryan Model 92. Following the expressed interest of the US Army in its development, a new designation emerged, VZ3, along with the fitting name Vertiplane. Over time, the military designation of the project was further supplemented with new letters, VZ3RY, under which it gained widespread recognition. The objective of the Vertiplane project was to construct an experimental aircraft capable of vertical or shortened takeoff and landing. It aimed to practically test original concepts that could significantly simplify the design. The experimental aircraft wasn't intended for payload carriage or weaponization, hence eliminating the necessity for high load capacity or specialized equipment. Only elements directly pertinent to the project's primary objectives were to exhibit comparative complexity. The proposed design for the VZ3 aircraft entailed a high wing configuration with two propellers mounted on underwing gondolas and a fixed landing gear. Its fuselage featured a large teardrop-shaped elongation. Notably, the nose and central sections of the fuselage, distinguished by an enlarged cross-section, boasted vertical sides and a horizontal bottom, seamlessly integrated with other surface areas. Additionally, the tail boom sported a tapering truncated cone shape. In the central part of the fuselage, flush with its upper surface, the wing of the original structure was attached. On the tail, it was planned to install a T-shaped tail unit with a small keel sweep and a rectangular stabilizer. The nose of the fuselage accommodated the cockpit for a single pilot. In the first version of the project, the pilot was to enter through a large opening between the roof and the sides of the fuselage. Even in the initial stages of the project, it became apparent that the cabin glazing design would not offer the necessary visibility during takeoff and landing. Consequently, an additional window with glazing was incorporated into the bottom of the nose fairing, enabling the pilot to maintain visual contact with the runway. The primary innovation of the Ryan VZ3 project lay in its unconventional wing design, featuring elaborate mechanization directly influencing the aircraft's key characteristics. The proposal involved installing a rectangular-shaped high-placed wing in the central part of the fuselage. Despite its relatively modest elongation, other design features compensated effectively for this limitation. Notably, the wing boasted a substantial profile thickness. Two small-sized gondolas housing gearboxes and propeller shafts were positioned beneath the wing. These gondolas featured large trapezoid-shaped combs aimed at mitigating airflow overflow and preventing it from exceeding prescribed limits. The experimental aircraft's wing featured sizable retractable flaps, comparable in area to the wing itself. To enhance takeoff and landing performance, these flaps could extend from the wing and tilt backwards, assuming a position close to vertical. Additionally, the wing, flaps and tip ridges formed a box-shaped system designed to significantly influence aerodynamics and effectively redistribute airflow. It was due to the redistribution of the flow and the direction of the air downwards that was supposed to get a shortened or even vertical takeoff. The experimental aircraft received an unusual power plant equipped with two propellers. The Avco Lycoming T53L1 turboshaft helicopter engine with a power output of 1,000 horsepower was situated in the rear fuselage. Air intake was facilitated through a bottom-mounted intake device and an internal channel of minimal length, while fuel was sourced from built-in tanks. A shaft positioned in front of the engine transmitted power to the central gearbox, which in turn distributed torque to two shafts running parallel to the wing spars. Subsequently, power was transferred to the propellers through a series of gears. 3 bladed propellers were affixed to the shafts emerging from the underwing gondolas, allowing for the gondolas to maintain a minimal size. Their width remained consistent with the pylons on which they were mounted, thereby minimizing obstruction of the plane's surface area. Each propeller boasted a diameter of 2.79 meters, effectively covering nearly the entire frontal projection area of the wing, thereby positively influencing flight performance. The experimental aircraft of this new model was designed to exhibit acceptable controllability across all flight modes. To achieve this, it was equipped with both traditional control surfaces and non-standard mechanisms serving similar purposes. Pitch and yaw control during speed flight modes were intended to be managed by the elevator and rudder respectively, situated on the stabilizer and keel. At low speeds, such devices sharply lost their efficiency, which, in addition to them, there was developed a system of gas rudders connected to the engine. The plane couldn't be completed with ailerons for this reason. The roll control was proposed to be carried out by changing the operating parameters of the 2 propellers. An increase in the thrust of one of the screws caused the corresponding plane to rise upwards under the action of the increased lift force and thus led to a change in roll. The initial version of the Ryan VZ3 Vertiplane project featured a 3-point chassis with a tailwheel. The primary supports of this chassis comprised 3 tubes of varying lengths, with wheels situated beneath the central fuselage section. A tail skid was positioned at the rear. Due to the aircraft's aim for minimal takeoff weight, provisions for retracting the chassis were not included. The dimensions of the first version of the aircraft were as follows: length 8.3 meters, wingspan 7.14 meters, height 3.25 meters. The normal takeoff weight was set at 1,180 kilograms, with the aircraft designed to be operated by a single pilot located in the forward cabin. The restricted takeoff weight constrained fuel capacity, with high speed and extended range not being primary project objectives. Instead, the focus was on achieving favorable takeoff and landing characteristics. The pilot project was completed in 1957, and by early the following year, the first prototype underwent testing. On February the 7th, it was transported to the airport for ground tests, which preceded its inaugural flight. Prior to this flight, extensive ground testing and wind tunnel trials were conducted over the course of nearly a year. The efforts yielded valuable insights into the aircraft's behavior across various modes of operation and identified areas for necessary improvements. According to the results of ground tests, an experienced aircraft was allowed to fly. The first flight of the experienced Vertiplane took place on January 21, 1959. The use of large flaps, together with the wing forming a box-like structure, gave certain results. In practice, it revealed the possibility of a sharp reduction in takeoff and run. At the same time, it wasn't without its problems. The initial challenges with the 1,000 horsepower engine became apparent early on, as it failed to generate the necessary thrust to take off without a sufficient headwind, resulting in extended run-up requirements. Furthermore, occasional handling issues arose under certain conditions. The primary focus of the test flights was to ascertain the actual performance characteristics during takeoff and landing modes. Evaluation of the aircraft's behavior in horizontal flight was of secondary importance. Testing revealed that the current configuration still couldn't execute vertical takeoff. Nevertheless, it showed promising potential for reducing run-up and runway requirements, albeit often reliant on favorable headwinds. Throughout the first months of 1959, Ryan Aeronautical and US Army specialists managed only about 24 relatively successful test flights. Unfortunately, during the 21st flight, the experimental VZ3 experienced a mishap resulting in damage. Despite this setback, the decision was made to restore the aircraft and continue testing. However, shortly after the accident and the commencement of repairs, the US military lost interest in the unconventional project and withdrew its participation. This decision was influenced by various factors, leading to a halt in further collaboration on the project. However, the aircraft was still needed by science, because of which, after repair, the prototype was transferred to NASA. Further work was carried out by the Aerospace Agency specialists. The tests were resumed in February 1960, but soon stopped again. During the next ascent into the air, there were problems that forced the pilot to leave the car. Fortunately, the aircraft sustained minimal damage and was deemed repairable. This presented an opportunity to implement several new solutions inspired by the breakdowns and subsequent repairs. The prototype wasn't merely restored, it was also reimagined according to an updated project plan. These enhancements were informed by ground and aerodynamic tests, as well as insights gained from the initial test flights. Foremost among the changes was a significant overhaul of the chassis. The design of the main landing gear underwent modifications, and the tail skid was replaced with a fixed nose strut. This adjustment altered the aircraft's stance on the ground and during takeoff runs, requiring it to rest level with a slight nose-down attitude. Refinements to the chassis, aimed at enhancing visibility during takeoff and landing, prompted the removal of glazing from the nose fairing. Furthermore, the cabin underwent a transformation, shedding its existing glazing and roof. Now, only a small visor remained to shield the pilot, with no additional elements of the canopy present. Additionally, a portion of the metal fuselage skin in the nose section was replaced with linen material. Measures were taken to change the aerodynamics of the aircraft. In place of the crutch under the fuselage, an additional comb appeared, which improved the stability along the course. To improve the characteristics of the wing, deviated slats appeared on the plane. Also changed were the size of the flaps. Various modifications were implemented to simplify or enhance specific elements of the aircraft and improve its aerodynamic performance. By the end of 1960, NASA experts once again brought the experienced Ryan Vertiplane to the runway. Inspections of the aircraft continued until 1961, primarily focusing on studying its takeoff and landing characteristics with different wing configurations, controllability in various modes, and other factors. Horizontal flight characteristics were also evaluated multiple times throughout the testing process. Over several stages of testing, interspersed with repairs, a wealth of diverse information was gathered. The prototype VZ3 was subjected to testing at speeds ranging from 6 knots (11.1 km an hour) to 80 knots (148.1 km an hour) and demonstrated acceptable performance across this spectrum. Optimal takeoff and landing parameters were achieved within the 20 to 25 knot range, 37 to 46 km an hour. For instance, at speeds of approximately 35 km an hour, the aircraft required 9 to 10 meters of runway, slightly more than its own length, to take off. Maintaining lift at this speed allowed the aircraft to ascend to an altitude of 1.1 kilometers. Early in the testing phase, pilots encountered the phenomenon known as ground effect. At altitudes below 5 meters, air currents reflecting off the ground began to adversely affect the operation of the propellers and the wing, reducing their efficiency. Additionally, aircraft stability diminished, potentially resulting in an uncontrolled dive and subsequent crash. Incorrect use of gas rudders exacerbated these risks during such conditions. The negative impact of the underlying surface particularly hampered the implementation of the landing. Nevertheless, recommendations were soon formed on the optimal modes of descent and touching the ground. To avoid loss of control and fall, the pilot on landing, dropping below 15 feet 5 meters, had to withstand speeds of around 20 knots. Maintaining a descent angle of several degrees was crucial during landing. Experimental trials pushed the landing speed to 40 knots, 74 km an hour, and the descent angle to 16 degrees, but such landing modes posed significant risks. From the initial wind tunnel tests, it was evident that the Ryan VZ3 Vertiplane, despite its name, would not be capable of vertical takeoff and landing, a conclusion confirmed during full flight tests. Nevertheless, the project's creators achieved a substantial reduction in runway length, aligning with the original project objectives. Testing of the prototype, revamped according to the updated project specifications, persisted until 1961. Following their conclusion, American experts meticulously analyzed the amassed data, producing numerous reports and scientific works. This comprehensive study spanned several years, shedding light on various aspects of the aircraft's performance. By this time, the prototype had been relegated to storage, with little hope of resuming flights. Indeed, after 1961, the experienced VZ3 never took to the skies again. After all of the required research and scientific work was completed, the car was decommissioned as superfluous. Unlike some other unique examples of aviation technology, the only Vertiplane was not dismantled for metal. The aircraft was handed over to the Army Aviation Museum, Fort Rucker, Alabama, where it remains to this day. It's worth noting that the prototype Ryan Model 92 VZ3 Vertiplane wasn't the sole platform dedicated to testing and refining innovative concepts aimed at enhancing aircraft takeoff and landing capabilities. Throughout the 1950s, numerous similar-purpose aircraft were developed and tested by several other US aircraft manufacturers. Like the VZ3, these aircraft merit separate examination and review for their contributions to advancing aviation technology in this regard. Gliding and soaring saw a surge in popularity across the United States from the early 1930s through the post-war era. Yet the challenges associated with getting a glider airborne deterred many potential enthusiasts. Glider pilots were presented with various options, all of which were relatively cumbersome and occasionally perilous, often requiring additional pilots, drivers, or ground crew. Among these methods, the most convenient involved taking off in tow behind either an automobile or a powered aircraft. In Germany, where gliding and soaring gained momentum shortly after World War I, groups of able-bodied individuals would sprint down hills, towing the motorless aircraft into the air using elastic bungee cords. While bungee launchers enjoyed considerable popularity in Europe, their adoption in North America was hindered by the wider availability of auto and airplane tows, alongside the region's hot and humid climate, which made this labour-intensive alternative less appealing. Powered winches were also utilised to tow gliders aloft, but this method posed risks and required a certain level of pilot proficiency. Additionally, it relied on a skilled winch operator. Once airborne, a pilot might opt to venture beyond the confines of the airport and embark on a cross-country journey, often culminating in a landing in a meadow or a field. Returning the glider to its home base necessitated significant group effort. The ground crew disassembled the glider into manageable sections, loaded them onto a specialized trailer, and transported them back by road. Glider enthusiasts found themselves dedicating more time to pre-flight preparations than actual flying, setting them apart from other aviation groups. Meanwhile, in the United States, William H. Bolus and Ted Nelson pioneered one of the earliest self-launching motor gliders. Bolus had already established himself as a proficient craftsman in glider design, with his BA-100 Baby Albatross and Senior Albatross models during the 1930s. Nelson, too, had developed several designs during this era. In 1945, they co-founded the Nelson Aircraft Corporation to manufacture a two-seat motor glider based on the popular Bolus BA-100 Baby Albatross. Dubbed the Bumblebee by the designers, it was officially marketed as the Dragonfly. While retaining the basic design of the Baby Albatross, Bolus and Nelson made significant modifications, such as widening the cockpit to accommodate side-by-side seating and adding individual flight controls for each occupant. They also incorporated improvements like tricycle landing gear with a steerable nose landing gear, additional vertical fins mounted on the horizontal stabilizer ends, and a hinged canopy. A pull-start handle for the engine was installed inside the cockpit. The aft section of the fuselage pod provided an ideal location for installing a pusher engine and propeller. Initially, Bolus and Nelson opted for a Reiter 4-cylinder 2-cycle engine known as the 4034. However, this engine only produced approximately 16 horsepower. This wasn't enough power for flight, so Nelson decided to build a suitable engine from scratch. His new motor boasted 25 horsepower, just enough for takeoff and a gradual ascent. Due to the limited horsepower, the engines could only drive small, lightweight propellers. However, this was deemed acceptable as larger propellers added weight and increased drag. A drawback of the smaller propellers was the necessity for them to rotate at very high revolutions per minute (RPM) to generate adequate thrust. For instance, Nelson's engine required 3,900 RPM to lift the Dragonfly off the ground. Unfortunately, this high-speed rotation made the smaller diameter propellers considerably less efficient compared to larger propellers turning at lower RPM. This power plant and propeller combination enabled the Dragonfly to climb at a rate of 235 feet per minute at sea level. However, the additional weight of the engine and the drag from the widened fuselage resulted in a mediocre lift-to-drag ratio for the Dragonfly. The self-launch capability came at the expense of performance, which deterred many prospective motor glider owners, leading to only 7 Dragonflies being sold by Bolus and Nelson. In 1949, Nelson made another attempt at designing a self-launching glider, this time collaborating with Harry Pearl, with assistance from Don Mitchell. In 1973, Charles R. Rhodes generously donated his Dragonfly to the National Air and Space Museum. In the late 1990s, preservation specialists at the Paul E. Garber facility made a surprising discovery regarding the airplane. They found that the individuals who flew this aircraft had altered the induction system on the Nelson engine, creating at least 3 distinct configurations. Additionally, they observed that the engine mounted on the motor glider was incomplete, lacking several essential electrical system parts. This led them to suspect that either the engine or parts of it had been exchanged for non-airworthy components before the donation. The B aircraft Honeybee was a single-seat, all-metal light aircraft crafted by William Channer and Kenneth Coward, engineers associated with Convair, formerly Consolidated Vultee, situated in San Diego, California, USA during the 1970s. Its inaugural flight took place on the 12th of July, 1952. Remarkably, this aircraft has endured the test of time and now stands proudly on display at the San Diego Air and Space Museum, having been generously donated by the American Experimental Aircraft Association. The founders of B-Craft Associated Incorporated were instrumental in the creation of several innovative designs. Amongst these was the WWII, a monoplane touted as large enough to carry a man, yet compact enough to be lifted by one. Demonstrated both in the United States and England, it secured a place in the Guinness Book of World Records as the world's lightest aircraft. Featuring a 2-cylinder engine and a tricycle undercarriage, the pilots assumed a prone position atop the fuselage. Following the success of the WWII, the Honeybee emerged, with the inaugural model completed in 1952. This single-seater boasted an enclosed cabin, a high cantilever monoplane wing, and a distinctive V-tail. The designers then ventured into crafting the Queen Bee, a 4-seater marvel, which was finalized in 1960, further cementing their legacy of innovation in aviation design. Eventually, the WWII and the Queen Bee were retired to the San Diego Aerospace Museum, but these 2 prototypes were destroyed by a fire at the museum premises on the 22nd of February 1978. The aircraft's structure featured simplified normal aircraft sheet metal, with a cantilever wing composed of flanged aluminum alloy ribs riveted to the main spar, covered by light-gauge aluminum skin. Its distinctive V or butterfly tail mirrored this construction, with control surfaces crafted from pressed fluted skins. The fuselage adopted a semi-monocoque structure, utilizing flanged aluminum frames and stringers, complemented by metal skin. Equipped with a tricycle undercarriage, the Honeybee featured a steerable nose leg and spring steel main legs. Typically, it was outfitted with a 48 kilowatt, 65 horsepower Continental engine, although various engine options were available. Notably, the Honeybee earned the distinction of being the first all-metal light aircraft design sanctioned by the Australian Department of Civil Aviation for construction by amateur builders. At least one such example was constructed in Australia. The earliest known instance of construction within the region occurred when students embarked on Project Honeybee at the Royal Melbourne Institute of Technology, VIC. Additionally, another Honeybee was in progress during the mid-1970s under the auspices of the Ultralight Association, Victorian Division. It's documented that the construction of a couple of other Honeybee aircraft was initiated. However, whether any of these projects were completed remains uncertain. If indeed completed, it's likely that they would have been operated under Ultralight or RAA, Recreational Aviation Australia, regulations. As of now, no photographs of these additional Honeybee aircraft have surfaced. From 1963 to 1975, a fleet of lifting bodies operated at NASA's Flight Research Center, now Armstrong Flight Research Center in Edwards, California, showcased the capability of pilots to maneuver and safely land a wingless vehicle. These lifting bodies were specifically designed to validate the concept of returning a wingless vehicle from space and executing an aircraft-like landing at a predetermined site. These pioneering research vehicles, distinguished by their unconventional aerodynamic shapes, included the M2F1, M2F2, M2F3, HL-10, X-24A, and the X-24B. The data gathered from the lifting body program significantly contributed to the knowledge base that ultimately facilitated the development of the Space Shuttle program. Unlike conventional aircraft that rely on wings for aerodynamic lift, these lifting bodies derive lift from their unique shapes. Fins and control surfaces were added to enable pilots to stabilize and maneuver the vehicles, effectively controlling their flight paths. With the exception of the M2F1, all of these vehicles were powered by the XLR-11 rocket engine, the same type used in the Bell X-1, which famously achieved supersonic flight, breaking the sound barrier for the first time. The M2F1, serving as a lightweight prototype, was unpowered. The original idea of lifting bodies was conceived around 1957 by Dr. Alfred J. Eggers Jr., then the Assistant Director for Research and Development Analysis and Planning at the Ames Aeronautical Laboratory, now NASA's Ames Research Center in California's Silicon Valley. H. Julian Allen, an engineer at Ames Research Center, concluded that a blunt nose cone shape was optimal for surviving the intense aerodynamic heating encountered during re-entry from space. The collective research efforts of Eggers, Allen, and their team culminated in the design of the M2, a modified half-cone shape characterized by a rounded bottom and a flat top, featuring a blunt, rounded nose and twin tail fins. This innovative configuration, along with subsequent lifting bodies, enabled them to be maneuvered both laterally and longitudinally, facilitating landings on runways rather than relying on ocean splashdowns typical of contemporary ballistic capsules used in programs like Mercury, Gemini, and Apollo. In 1962, Flight Research Center Director Paul Bickle greenlit a program aimed at constructing a lightweight, unpowered lifting body to serve as a prototype for testing the wingless concept. Resembling a flying bathtub, this prototype was designated the M2F1. Crafted by sailplane designer Gus Briegleb, the M2F1 featured a plywood shell enveloping a tubular steel frame meticulously assembled at the center. Construction reached completion in 1963. The initial flight trials involved towing the M2F1 aloft using a souped-up Pontiac convertible, reaching speeds of up to 120 miles per hour across Rogers Dry Lake. These early tests yielded sufficient flight data about the M2F1, paving the way for subsequent flights behind a NASA R4D towplane at higher altitudes. The R4D, a Navy designation for the C-47 or civilian DC-3 aircraft, towed the craft to an altitude of 12,000 feet, where it was then released to soar freely back to Rogers Dry Lake, marking a significant milestone in the experimental journey of the M2F1 lifting body. NASA research pilot Milt Thompson flew the M2F1 during the first series of tests. During typical glide flights with the M2F1, the aircraft would remain airborne for several minutes, cruising at speeds ranging from 110 to 120 miles per hour. Remarkably, the M2F1 underwent over 400 ground tows and 77 aircraft tow flights before being retired from active service. Today, this significant historical artifact is under the ownership of the Smithsonian's National Air and Space Museum. Currently, it's on a long-term loan to NASA Armstrong, where it has undergone meticulous restoration to resemble its flight-worthy condition, allowing future generations to appreciate its pioneering contributions to aerospace research and development. The success achieved through the M2F1 program spurred NASA to embark on the development and construction of two heavyweight lifting bodies, drawing from studies conducted at NASA's Ames and Langley research centers. These lifting bodies were the M2F2 and the HL-10, both of which were manufactured by Northrop Corporation. In the nomenclature, the M denotes manned, while the F signifies flight. The HL designation originates from horizontal landing, with the number 10 indicating the 10th lifting body design explored by Langley. Subsequently, the US Air Force also expressed interest in lifting body research, leading to the creation of a third design concept known as the X-24A, fabricated by the Martin Company. This model underwent modifications to become the X-24B, with both configurations actively participating in the joint NASA Air Force lifting body program at the Flight Research Center. The fundamental flight profile of these heavyweight lifting bodies involved air launching from NASA's modified NB-52B mothership at an altitude of approximately 45,000 feet, marking the commencement of their experimental flight missions. The XLR-11 rocket engine was then ignited and the vehicle accelerated to speeds of up to 1,100 miles per hour and to altitudes of 60,000 to 70,000 feet. After the rocket engine was shut down, the pilots began steep glides towards the Edwards runway. As the pilots initiated the final approach leg, they augmented their rate of descent to accelerate and harness momentum, executing a flare-out maneuver to decelerate their landing speed to approximately 200 miles per hour, mirroring the basic approach pattern and landing speed utilized by today's space shuttles. The inaugural flight of the M2F2, which closely resembled the M2F1, took place on July 12, 1966, with Milt Thompson once again at the controls. By this time, the same B-52 aircraft responsible for air launching the renowned X-15 rocket research craft had been adapted to also accommodate the lifting bodies. The M2F2 was released from the B-52's wing pylon mount at an altitude of 45,000 feet during its maiden glide flight. The M2F2, weighing in at 4,620 pounds without ballast, measured approximately 22 feet in length and boasted a width of about 10 feet. Tragically, on May 10, 1967, during the 16th glide flight, a landing mishap resulted in severe damage to the vehicle and inflicted serious injuries upon the NASA pilot Bruce Peterson. NASA pilots identified lateral control issues as a contributing factor to the crash of the M2F2, despite the presence of a stability augmentation control system. Subsequently, when the M2F2 underwent reconstruction and was rebranded as the M2F3, enhancements were made to rectify these concerns. One notable modification included the addition of a third vertical fin, strategically positioned between the tip fins to enhance control characteristics. The maiden flight of the revamped M2F3 occurred on June 2, 1970, with NASA pilot Bill Danner at the helm. This initial flight was a glide test aimed at assessing the performance changes resulting from the modifications. Notably, the modified vehicle demonstrated significantly improved lateral stability and control attributes compared to its predecessor, the M2F2. Over the course of the subsequent 26 missions, the M2F3 achieved remarkable milestones. It reached a top speed of 1,064 miles per hour, equivalent to Mach 1.6, with Danner piloting a high-speed mission on December 13, 1972. On December 20, 1972, during its final flight with NASA pilot John Mank in command, the M2F3 attained its highest altitude of 71,500 feet before concluding its operational tenure. Today, the M2F3 stands proudly on display at the National Air and Space Museum in Washington, serving as a testament to its pivotal role in aerospace history and its contributions to the advancement of flight technology. The HL-10, delivered to the Flight Research Center by Northrop in January 1966, took to the skies for its maiden flight approximately 11 months later, on December 22nd of the same year, piloted by Bruce Peterson prior to his injury in the M2F2 accident. Over the course of its operational tenure, the HL-10 completed 37 flights, setting numerous program records along the way. Peter Hogue piloted the HL-10 to a remarkable speed of 1,228 miles per hour, equivalent to Mach 1.86, marking the fastest speed achieved by any of the lifting bodies. Just 9 days later, NASA's Bill Danner guided the HL-10 to an impressive altitude of 90,303 feet, establishing the highest altitude reached by any of the lifting body aircraft. Furthermore, on May 9, 1969, under the command of pilot John Mank, the HL-10 became the first lifting body to achieve supersonic flight. Featuring a longitudinally curved bottom and a laterally rounded top, the HL-10 sported a distinctive delta planform. In its final configuration, directional control was facilitated by 3 vertical fins, 2 of which were canted outward from the body, accompanied by a tall center fin. A flush canopy blended into the smooth, rounded nose. It was about 21 feet long, with a span of 13.6 feet. Its glide flight weight was 6,473 pounds, and its maximum gross weight was more than 10,000 pounds. The flights of the HL-10 played a significant role in shaping the design decisions for the space shuttles, particularly in the exclusion of air-breathing engines for powered landings. The HL-10 concluded its operational flights on July 17, 1970, marking the end of its remarkable journey. Today, this iconic craft stands proudly on public display at the entrance to NASA Armstrong Flight Research Center, serving as a tangible reminder of its invaluable contributions to aerospace research and development.
August 6, 1945. The day warfare changes irreversibly. It is not the result of a battleship or a fighter plane. Instead, it comes from a device less than 10 feet in length and 3 feet in width. Dropped from a B-29 superfortress, the bomb known as Little Boy is the first atomic weapon to be used in history. Alongside its accomplice, Fat Man, these 2 weapons of mass destruction pulverize the Japanese, as 2 cities are obliterated. Now, the world led by the United States and the Soviet Union enter a new and frightening age where just 1 bomb can wipe out an entire population. With the Second World War ending and the Cold War beginning, America and the Communists start a massive buildup of this new technology. The race is on, where whoever possesses the most deadly arsenal of atomic force prevails. On both sides of the Iron Curtain, nuclear weapons become the ultimate symbol of strength and might. And during this period of intense Cold War anxiety, the idea of having aircraft fueled by this new source of energy is given the green light. If a nation can power homes and submarines with nuclear power, will planes be next? Having an atomic reactor on board has endless possibilities. Unlimited range, and the ability to be anywhere in the world in a matter of hours, ready to strike. Truly awesome aviation that will determine the #1 superpower. Unfortunately, this concept is easier said than done. Placing a nuclear device on an aircraft is both complicated and extremely dangerous. Can American scientists and aircraft designers overcome these obstacles? Can they prove the skeptics wrong? This is their story. The United States' decade-long saga to produce the first nuclear-powered aircraft. Prepare to experience the atomic-powered plane.
We are gathered here, representatives of the major warring powers, conclude a solemn agreement whereby peace may be restored.
With the Japanese surrender on the USS Missouri, Americans are both victorious and confident. The war they have been fighting for over 3 years has finally ended. They have emerged a superpower with what seems to be an unlimited industrial capacity. The nations of Europe are no longer the power brokers they once were, for it is the United States and its ally the Soviet Union that remained strong at the end of the Second World War. But just as this conflict ends, a new and more deadly struggle begins, as Nazism is replaced by communism as the greatest threat to Western democracies.
Nobody really knew a grand vision for Europe, even as Nazi Germany collapsed. there were still large questions as to territory, peoples, the movement of peoples, and exactly how this would all work out. The grand strategy with Franklin Roosevelt's the famous spheres of influence, which means nothing, everything and nothing at exactly the same time, and that's where the roots of the Cold War come in big. There was a lot of tension and a lot of questions on both sides as to how it would all work out.
With this shift in the balance of power, the Soviets are no longer America's ally. They are now the enemy. And for the next 50 years, tensions between the two superpowers are felt beyond the capitals of Moscow and Washington, D.C., as the world is divided between capitalist and communist. Whoever can win the hearts and minds of those around the globe will emerge victorious. As this new Cold War takes shape, people begin to realize that America's victory over Japan has become a double-edged sword. The dropping of an atomic bomb, the nuclear genie has been let out of the bottle.
Well, world reaction was stunned. I mean, this is, I think, even at the time and place, a realization that it was a monumental event, even though nobody really understood what had taken place scientifically or even politically, even with respect to the war. It was unclear. But I think most people understood, and my read of the press in particular at the time was an acknowledgement that this was really big. This wasn't just any sort of military adventure whatsoever. But it's important to keep in mind that almost nobody, including the men who made the decision to drop it and the scientists who worked on the project, understood its ramifications in full. And I think it's useful to, remember Einstein, right, saying, I don't know how they're going to fight this war, but I guarantee you how they'll fight the next with sticks and stones.
Fearing the Soviets will be next, Russian scientists begin a mad rush to acquire this technology. What the United States possesses, they must equal and better it. It is unlike any other arms race in history. The end result could potentially wipe out 1/2 of the world's population, and even more. For this reason, it is vital that both nations attain as much nuclear technology as possible to deter the other from striking. As a result, rigorous testing is done on both the American mainland and on strategic outposts like Bikini Atoll.
The B-29 Dave's Dream takes off from Kwajalein to deliver the bomb, equal to 50,000 tons of TNT, while an electric metronome counts the final seconds. Cover your eyes. Now, on the way.
To calm public fear of atomic power, every attempt is made by the United States government to emphasize the positive aspects of this new source of energy. Nuclear power plants are constructed across the country as a sign of progress and achievement. President Eisenhower goes to the United Nations with the idea of using atoms for peace.
The United States pledges before you, and therefore before the world, its determination to help solve the fearful atomic dilemma, to devote its entire heart and mind to find the way by which the miraculous inventiveness of man shall not be dedicated to his death, but consecrated to his life.
You have to understand the atomic aircraft project as part of the pentomic era. The 1950s, late 40s and early 50s, when everything that could be atomic was being turned into an atomic thing. There was atoms for peace. There was the idea that energy would be so cheap you couldn't meter it. You wouldn't have to meter it. Anything that could be powered by the atom was to be powered.
Despite these efforts, many are still skeptical about this source of power and its deadly ramifications. These fears are amplified with the development of Project Pluto, a nuclear-powered missile designed to unleash fission fragments all over the Soviet Union. Dubbed the Flying Crowbar, this weapon is considered too extreme even for the most hawkish Cold Warrior and is abruptly cancelled. Looking at the carnage of Hiroshima and Nagasaki, Numerous Americans fear this technology throughout the 1950s.
What's it like, Chaplain? First of all, one sees a very, very bright light, followed by a shock wave, and then you hear the sound of the blast, and then it seems as though there's a minor earthquake. And then you look up and you see the fireball as it ascends up into the heavens. It contains all of the rich colors of the rainbow, and then as it rises up into the atmosphere, it turns a beautiful pale yellow, and then assembled into the mushroom. It's a wonderful sight to behold.
Hoping to end these concerns, in January of 1954, the USS Nautilus becomes the first naval vessel to safely enter the nuclear realm. With an atomic reactor powering the submarine, it can stay submerged for months if necessary, giving the United States a huge advantage over the Soviets in case trouble erupts. With this advancement, many are asking if it can work for an airplane as well.
And that's what somebody got the bad idea. Well, nuclear power, you can run a submarine, why can't you run an airplane?
Much will be learned here of the workings of atomic engines, not only for submarines, but for many peacetime uses as well. For passenger and merchant ships, for land transportation, for electric power plants, even perhaps for the huge airplanes of the future.
Submarines are not constrained by the same weight limitations as an airplane. So you could put a 10-ton reactor in with 100 tons of shielding, all wrapped around it in something that need only float. It's a completely different physics principle. And so therefore you have the space in the submarine for large reactors, large shielding, and large cooling systems.
It appears that what the Navy has been able to accomplish, the Air Force is going to have a harder time replicating. Despite all the doubts and skepticism, the decision to combine atomic energy with aviation is approved. Just like how the Liberators and flying fortresses that destroyed German cities mercilessly played an enormous part in winning the war in Europe, and how the constant bombardment of Japanese cities by B-29s was essential to American victory in the Pacific, perhaps a new bomber powered by nuclear energy will defeat the Soviets. For this reason, it comes as no surprise that many inside Air Force circles are eager to have a plane powered by the atom up in the skies as soon as possible. Across the Atlantic Ocean, the United States Navy hopes the same Anglo-American cooperation that produced the P-51 Mustang can result in their own version of a nuclear aircraft. Looking for the biggest plane Britannia can offer, both countries study the possibility of converting the gigantic Saunders-Roe Princess flying boat, a plane whose time has passed, into a device given its second wind by nuclear power. A key advantage of this concept is its range. Just 1 pound of uranium-235 is the equivalent of over 250,000 gallons of jet fuel.
With the end of World War II and the start of the Cold War, they now needed a bomber that could reach the Soviet Union from the United States. A nuclear-powered aircraft would not be limited by a fuel load, so it was desirable from that point of view.
With 30 million horsepower, theoretically, the aircraft could be up in the skies far longer than any conventional bomber in the US's arsenal.
Would sort of loiter over somewhere, US soil, presumably for days or weeks on end, possibly. Sort of simply be there as a warning.
So despite fears of nuclear annihilation, both the Air Force and the American government approved the project to develop this plane. In May of 1946, the Nuclear Energy for the Propulsion of Aircraft, or NEPA, is created. Where in the secret atomic city of Oak Ridge, Tennessee, the first stages of development begin. Looking for a company to start testing, Washington goes to one of its very best, Convair, makers of the massive B-36 Peacemaker. They are awarded the contract to begin designing their version of the atomic-powered plane, which after more than a decade of research and development, they dub the NX-2. an aircraft that looks eerily similar to North American Aviation's B-70 Valkyrie. The question is whether they'll use a B-36 or the new revolutionary jet-powered B-60 to begin their preliminary tests. An act of divine intervention makes this an easy decision for Convair when a tornado rips through Carswell Air Force Base, damaging a fleet of peacemakers. With little to lose, it is after this natural disaster when the choice is made to repair one of the B-36s, named the Crusader, and turn it into a nuclear-powered bomber under the Plan X6, with the General Electric Corporation chosen as the company to build its reactor.
The US Air Force had a nuclear reactor installed aboard a Convair B-36 bomber. The nuclear reactor did not fly the aircraft. It had its own engine that was simply there as an experiment to see, for example, the thickness of shielding required to protect the crew from long-term exposure to radiation.
A key roadblock in the plane's development comes from the radiation it will emit. Anyone standing within 100 feet of the core reactor unprotected is in store for a lethal dose of radioactivity. On land, nuclear power plants are shielded by more than 6 feet of concrete. In the skies, however, this shielding is too heavy for any aircraft, including the B-36, to sustain.
The single largest problem with an atomic-powered aircraft is that a reactor requires much shielding. Roughly for every ton of reactor, you require 10 tons of shielding. This was the case in the NV-36 program. A relatively small reactor required a cockpit shielded with 12 tons of lead and lead crystal glass just to protect the crew from the radiation emitted by the reactor.
And for it to be economically feasible, it must be able to carry a payload bigger than the B-52. For nuclear aviation to become reality, these barriers must be overcome by its designers. With this in mind, Convair's still unbuilt NX-2 places its pilots and crew far away from the reactor, hopes that less shielding will be required. But even if this is accomplished, there are still questions surrounding the heat generated on board the plane. Producing more radiation than a nuclear power plant into such a contained space has scientists worried that the intense temperatures are going to melt away the aircraft's interior.
There was no real way at the time to fix these problems, much as there isn't now. The shielding still grossly outweighs the reactor, and it turns out there's really no need for it.
Just like the Navy and its Princess flying boat, the Air Force is slowly realizing that the plane and the atom don't mix. Adding to these problems is many people's fear with all things nuclear. With the possibility of an entire city being wiped out with the flip of a switch, there are grave concerns over what happens if the plane crashes. If a hot reactor falls on a heavily populated area, the civilian casualties could be enormous. With this in mind, every precaution is taken when the NB-36 is sent out on a test flight.
We had a B-50 as a chase airplane to follow us in flight. Then they decided if we had to, for instance, an accident, what were we going to do? Well, they decided we better have some paratroopers to follow us down. We had C-19 to carry paratroopers. And we landed. All of this was secret.
Eventually, for a number of reasons, safety, cost, practicality, the nuclear-powered aircraft never got off the ground.
With this concept all but dead, it is miraculously brought back to life when a report surfaces that the Soviets are building their own version of an atomic-powered plane, in the form of a modified Tupolev 95.
One of the big pushes for this project happened after the NB-36 had stopped flying. In December 1958, the very important magazine Aviation Week, now called Aviation Week in Space Technology, published an editorial with photographs that they said were of an atomic-powered aircraft being flown in the Soviet Union. They had these drawings that even showed the big red stars on the side of the aircraft. Turned out to be a complete falsehood, a complete lie, and it's now thought that it was put out by the contractors and the Joint Committee on Atomic Energy, who were trying to push the atomic aircraft program through Congress and to force the U.S. Air Force to accept it.
Many of the cutbacks have not been justified. I would not want to condemn all. I know one which I regard as very damaging indeed, the cutback and the stretch out of the atomic airplane program. If our technicians were permitted the money and the authority to go ahead, they could fly an atom plane next year. Under the Take It Easy program of the administration, however, we are not scheduled to fly an atomic plane before 1964, if then. I doubt if the Russians will wait that long.
Afraid of another Sputnik, the American government assures its people that with each passing year, a nuclear-powered aircraft becomes more of a reality. While behind the scenes, its designers know the project is impossible to achieve. One major blow comes from President Eisenhower, who fights to end this plane before it consumes hundreds of millions of dollars more in appropriations. But perhaps the biggest nail in the NX-2's coffin comes from a Boeing -80 prototype.
In 1957, the last year that the NB-36 was flown, the U.S. Air Force introduced its first KC-135 tankers. 3 years later, they had 400 of these aircraft, servicing as airborne refueling stations for B-52s. They could now reach any part of the Soviet Union from the United States without landing. The idea that you now needed a reactor to do this was over, and the U.S. government realized the project was essentially dead because they already had the bomber force that they wanted.
With KC-135s and B-52 Stratofortresses, by the end of the 1950s, patience is wearing thin for a nuclear-powered bomber. After spending more than $500 million, and with no end in sight, the project is now on the chopping block. As one politician is overheard saying, it has been marked by a lack of well-defined objectives and by administration indecision. The optimism of the late 1940s and early 1950s has vanished. And when a Defense Department official tells the media that the plane's price tag will be over $10 billion when finally completed, the NX-2's days are numbered.
The world is very different now.
In 1961, as the Eisenhower era ends and John F. Kennedy is sworn into office, the project receives its final nail in the coffin when the aircraft, like many other Cold War creations, is terminated.
At the end of the day, heavy atomic reactors don't really belong on aircraft. And aircraft with refueling can reach their targets anywhere in the world. A reactor was simply found unnecessary to do the job the U.S. Air Force wanted to do.
Like many other Cold War concoctions, the atomic-powered plane represented thinking big. During a time when many thought that nuclear energy was the future for transportation, it was almost inevitable that an endeavor of this magnitude would be undertaken. With America and the Soviets on the brink of complete annihilation, aircraft like these were given the go-ahead, despite its impossibilities. In the end, the atomic-powered aircraft became the quintessential example of a military-industrial complex run amok, where profits were placed above people, and where Convair was placed above common sense.
From 1933 until the end of the Second World War, German aviation led the world in aerodynamic design and technical innovation. Long before the outbreak of hostilities, German industry produced an armada of technically superior warplanes. When war broke out, the Luftwaffe quickly overwhelmed some of Europe's most vaunted air forces. Classic designs like the Bf-109 fighter and Ju-88 proved to be superior fighting machines, while others like the Blumenvoss BV-141 became one of aviation's true oddities. Germany's plan for war in Europe called for an air force that was to be used in direct support of its ground forces. The Luftwaffe's task was to sweep the skies clear of enemy fighters, then destroy enemy troops and installations. Key to the Luftwaffe's success were ground attack aircraft like the Henschel 123 and JU-87 dive bomber. Ordered in 1934, the Henschel 123 proved to be a rugged and reliable aircraft. It would see service well into 1944. Ground attack was only effective when good battlefield observation and reconnaissance could locate enemy targets. That job was given to the Henschel 126. With its excellent low-speed, short-field characteristics and outstanding all-round view, the HS-126 proved a great success in the early campaigns of 1939 and 1940. The HS-126 would see action on every front, but by 1941 its limited performance was beginning to show, and a new battlefield reconnaissance aircraft was needed. This led to some of the war's most unusual designs. The Blum & Voss company was one of the first to respond with their BV-141. Designed around the concept of maximum all-round view, the BV-141 was in many ways a problem looking for a solution. The unorthodox design featured an asymmetric layout with the radial engine installed at the front end of a portside tail boom and an extensively glazed crew nacelle mounted to starboard. Unusual and radical in design, the BV-141 performed surprisingly well, but in the end it was considered too unconventional and it was cancelled in 1943.
Yes, in my meanderings throughout Germany, just after the capitulation, I was looking for unusual or advanced technology aircraft. And the 141 intrigued me a little, but I had heard that they were at an airfield called Grossenhain, which was quite near Meissen. There was a big reconnaissance unit which had many reconnaissance types of aircraft, and I thought maybe the 141 will appear there. So I flew there, and there was no sign of one, but I asked if I could speak to some of the POWs who were in the cage there, and one of the chaps told me that a 141 had indeed been there, but the last he remembered of it was not too long ago. It had had an engine problem while flying nearby and had landed on an emergency strip east of Grossenhain. So I flew over in that direction looking for this strip. But it wasn't really a strip I found, it was a small airfield. And it was, by this time I'd moved into the Russian occupation zone. And I decided to land there because I had already found that at that stage after the war, the Russians were still very amenable to the Brits because we had come in at the early stages of the war to help them. Anyway, when I landed, there weren't a lot of aircraft there, and there was a Russian commissar and with an interpreter, and I asked if there was a 141 there. He didn't really know things like the aircraft numbers, but he said there were one or two aircraft left, but his people had examined the airfield, taken away what they wanted, and the rest was left for destruction. So I said, could I have a look around, see what it was? He said, well, yes, why not? Because it's all going to be destroyed anyway. And in one hangar, there was indeed a 141. It had regularly had its engines run up by Feldwebel, who was available. And I said to him, was the aircraft flyable? And he declared, oh, yes, it was. I rather suspected his motive, so I wasn't too sure of what he was saying or believing what he was saying, because I think he had hoped I would fly him out of there and out of the Russian zone. But the Russians were obviously not going to play with that. Anyway, I thought I'll take his word for it and have a go at this. And the Commissar didn't object. He said, as long as I stayed within sight of the airfield, and I'd only have enough fuel to do that, he didn't mind, because it was due for destruction anyway. And so he let me fly that, and I had about 30 to 40 minutes in it to try out this theory that it flew very nicely in a straight line when on an angle of bank of 90 degrees. And after about 2 or 3 goes at this at various speeds and heights, I had trouble with the engine. So I had to return to base. And so I formed an impression that it probably did what it said it could do, but its real reason for failing, in my opinion, was it certainly wasn't an aircraft in the same category of handling as the Focke-Wulf 189, which I had already flown and was its competitor.
Another odd-looking aircraft was the Focke-Wulf 189. The completely glazed central nacelle, twin engines and tail booms were considered too radical for conservative Luftwaffe officials. Performance, however, won the day. Known as the Flying Eye, the FW-189 proved supremely versatile, universally popular, and one of the most reliable aircraft ever to see Luftwaffe service. During combat operations, the FW-189 surpassed all expectations. Despite flying low over the battlefield and taking large amounts of damage, it had the ability to absorb punishment and fight another day.
So I think that killed it more than the theory that it gave the gunner a wonderful field of fire by having no starboard half of the tailplane and being asymmetrically offset to give a clear field of fire to the gunner. So that was my experience of it. Not very impressive, but interesting. The Arado 234 was a beautiful looking airplane. Aesthetically, it was very clean and looked dynamic, aerodynamically, very attractive. And the cockpit was unusual. It was a glass cockpit right at the nose, and it reminded me, when I got into it, rather of like being in a helicopter. You were stuck right out in the front there with completely clear vision around you. On the other hand, you were sitting pretty close to the accident if it had to happen too. And my first meeting with the 234 wasn't a very happy event, because this was up at Grover in Denmark, where we found a number of 234s, and I had one prepared for a flight by the German crew, because we obviously didn't have the expertise to deal with it at that stage. And I taxied it out to the end of the runway. I was well aware, of course, that the Jumo 004 engines, so fitted to it, had a scrap life, total scrap life of 25 hours. So one really needed to know the service history of the engines you were flying. Now, the Germans were very, very adept at destroying documentation, and we could find no service records. However, I taxied out to the end of the runway at Grover and revved up to full power, ready for takeoff, and then just about to release the brakes when the starboard engine exploded and totally disintegrated, taking most of the starboard wing with it. And this, of course, could have meant one of two things. Either the crew had sabotaged it, or it was an engine with 24 hours and 50 minutes on it. We never got to the bottom of what caused it, but suffice it to say that I must have flown something like 300 to 400 hours on the JU290 and various aircraft, and never had another problem with it after that. So it did not give me a poor impression, the 234. On the contrary, when I flew it, it was a very nice aircraft to handle, at a very fast turn of speed. It could fly at cruise, its top speed was 474 miles an hour, which was very high. And of course, it relied on this speed for its survival, because it had no guns fitted to it, and was purely a reconnaissance bomber as such. But as I say, handled beautifully. It was straight wing, was not swept wing, and made a very good impression.
Juncker's JU-52, affectionately known by those who flew her as Iron Annie, or Auntie U, or simply Auntie. The tri-motored transport, which also served as a bomber, was to become a legend, not only for her longevity, but also for her flexibility. She was in fact as much a symbol of the Luftwaffe as the Stuka and the 109.
The JU-52 was like the DC 2 and 3, I would say an iconic aircraft, because its reliability, it's three-engine aircraft, very, very reliable, and one wonders why they weren't more frequently used in the UK and the USA, three-engine layout, because it was very common in Italy, was used quite widely in Germany, and but you just have rare cases of it in the States, like the tri-motor Ford, but it's a great solution.
The JU-52 was constructed with the same corrugated material that the Junkers company was to rely upon for over 2 decades, going back almost to the Great War. During this period, aircraft much larger than the 52, such as the Behemoth Junker G38, also used the same cladding. However, as the 30s came to a close, Junker's corrugated hallmark was starting to look a little tired, especially compared with other foreign types like the American DC-2 and DC-3. Nevertheless, Auntie still stayed in service. The Junkers company had in fact designed a replacement for Auntie prior to the start of World War II. Although they still wanted to retain its tri-motor configuration, it was in most other respects a totally new aircraft.
The JU252. It was a distinct difference from the very famous JU-52. It had smooth thrust wings and a very large cargo fuselage capacity. One of the main features about it was it had a wonderful loading ramp, which was operated hydraulically at the back end of the aeroplane. Now, this was a tail-wheel aeroplane, but after landing, the ramp could be operated and would come down and raise the aircraft's tail. And it was absolutely top-notch. And the incredible thing about it was we actually did experiments to see how this thing would react on the airplane in flight. And at the large enemy aircraft exhibition in October of 1945, we flew this aircraft with the ramp fully open, and as a gimmick, we had a chap sitting on one of the lower steps on the ramp, obviously with a harness attached, but he was sitting there pretending to smoke a cigarette. Well, it appealed very heavily to the crowds, and it was quite surprising that this aircraft had this tremendous range of central gravity and was very trimmable in that situation.
The JU252 had a stablemate, the JU352, which was made largely of wood to reduce the use of aluminum. The JU352 proved less successful, although they were the first transport types to use a tailgate ramp that provided a flat surface for loading. Between the two models, only 65 examples were actually produced. When Germany was attacked on two fronts in 1944, they went out of production, as the priority was more fighters to defend the fatherland. Another military transport which used a rear ramp also came from the drafting boards of Junkers. The JU290 evolved from the four-engine Junkers 90 airliner, which showed great promise as an advanced design just before the war. The JU90 airliner, like most other aircraft of the time, was a tail dragger. So when Junkers created a transport version, they employed the same lifting tailgate developed for the earlier 252. For the time, the JU290 transport was a large aircraft when it first came into service in August of 1942.
When I flew the JU290, I was very impressed with it, in the sense that it had a lovely cockpit layout, a very comfortable layout. It was obviously a civil aircraft adapted to a military role, rather like the Focke-Wulf 200. It was almost similarly armed, not quite so heavily armed as the Focke-Wulf 200, but flew very nicely, and I think it would have made a comfortable, with a little adaptation, a comfortable transatlantic piston engine aircraft in the early days. In fact, after the war, of course, the Americans, they had a group like I had, retrieving aircraft, German aircraft after the war. They were called Watson's Whizzers. And Colonel Watson actually flew the JU290 back to America via Bermuda. And he was very impressed with it, as indeed I was too.
It was certainly the largest land-based powered aircraft in the Luftwaffe inventory. The type was 8 foot longer than the airliner version, had more powerful engines, and a very considerable range. It had been claimed, although never proven, that it made direct flights between Germany and Japan. There was also a need for smaller transports, even smaller than Anti-U. This need was filled by the conversion of a medium-sized glider into a powered aircraft. The Gotha 244 became available in 1943, created by the simple addition of 2 small radial engines to a standard production glider. The radials were actually made in occupied France, and as such had little impact on German war production. About 130 of the type were made and proved useful in moving small numbers of troops or light vehicles over short distances. Using the same glider to power plane conversion, the massive Messerschmitt 323 was another attempt to maximize the Luftwaffe's airborne assets.
The Gigant, I saw the 4-engine version and the 6-engine version of the Gigant. In fact, I taxied the 6-engine version. It wasn't airworthy, but I taxied it just as a matter of interest. It was a vast airplane, or glider, of course, and the one I taxied was the D model, and it had 6 gnome-rome engines, and the 4-engine one had proved difficult, inadequate number of engines, and still had to have some assisted takeoff, such as JETO, or rocket assistance on takeoff. As pure gliders towed by aircraft like the Heinkel 111Z, they were a failure, in my opinion. You had 3 Heinkel aircraft playing around with this, or the large Z, and all of them, the whole thing was a very dicey operation indeed. But once you got the 6-engine version going, it was practicable, but of course it was a large, sluggish airplane.
Because of its great size and slow speed, the Me-323 was a sitting duck, and many were destroyed by the Allies. But when escorted by fighters, its ability to carry large loads was much valued by the Wehrmacht, especially in the mayhem that became the Eastern Front. Blum & Voss built another remarkable transport aircraft, a long-range flying boat named the Viking. The BV-222 story is not unlike the JU-90s. It was originally ordered as a commercial flying boat. However, as the war approached, the Viking evolved into a large military transport, which also performed some patrol duties. 6 powerful engines propelled the Viking. At first, they were fueled with gasoline, but the BV-222 was intended to be refueled at sea by submarines. Since U-boats are driven by diesel, the practical solution was to convert the Viking to diesel engines. Blum & Voss had another prototype flying boat that was even more advanced. The BV-238 was designed to cope with harsher sea conditions than the Viking could handle. Working only with U-boats, it was expected to go on very lengthy missions. It was designed to be almost self-supporting and able to deal with many types of heavy cargo. To assist in loading the 238, it was equipped with a massive forward waterproof door in the bow. This could be employed in a similar manner to landing craft on a beachhead. What you see here is only a service hatch set within the waterproof door. To assist in handling cargo, there were derricks and winches located on the hull, making the BV-238 more like a merchant ship than an aircraft. There was also a tunnel which ran the length of both wings, providing internal access to the 6 engines, even when the flying boat was in the air. Only one BV-238 was completed. It was destroyed by Allied fighters just before the end of the war. The final example of Luftwaffe gigantism came in the form of the Junkers 390, a stretch 290 with a very capacious 110 feet long fuselage. Propelling this enormous aircraft would require 2 more engines than the JU290 and a much greater wing, over 160 feet in span. The extra wing length actually required an additional set of wheels on each side to support the craft as it landed. Only 2 Junkers 390s were ever built, but even these required enormous resources both in labor and material. After the war, only one of the JU390s was ever accounted for. This led to speculation as to what happened to the other aircraft, as the type had more range than any other German plane. When they already had a proven workhorse in the JU-52, why did the Third Reich become so preoccupied with limited numbers of large transport aircraft? One possibility was that Germany had not prepared for a long war. The premise of Blitzkrieg was achieving quick victory by lightning attacks. The English Channel stymied Blitzkrieg against Britain. With the rapid fall of France, crossing the Channel became the Wehrmacht's primary objective. This could partially be achieved by gliders, which led to large transport planes like the Gigant. Often overlooked, there was one other design that evolved in the fatherland during those turbulent years. The Arado 232, sometimes called the Millipede. Just after Germany invaded Poland, the Air Ministry issued a request for a replacement for the Ju-52. It must be equipped with a rear entry ramp and would employ two of the recently developed BMW 801 radial engines. Arado designers quickly came up with a brilliant design that embraced all the latest thinking in transport aircraft. It had a rear loading ramp, but unlike most other medium-sized transports of the time, it used a tricycle undercarriage. This type of wheel arrangement would not usually work in rough terrain. However, Arado engineers solved the problem by placing a row of small rollers under each side of the fuselage. If necessary, the main gear could be adjusted to kneel the plane down. The 232 would then simply crawl over obstacles on its many rollers, which led to its nickname, the Millipede.
At the end of World War II, we were, of course, interested in bringing quite a lot of heavy stuff back from Germany, like wind tunnel gear and even airplanes. And we were looking for cargo planes. We used a German aircraft called the Arado 232, known as the Millipede because of the large number of bogie wheels that it had as part of its undercarriage layout. And this was a most effective system of operating on grass airfields, which abounded in Germany in the early stages, and where traction was very difficult to find under adverse weather conditions.
The Millipede's level loading ramp made it ideal for all types of cargo. But the Arado 232 had a major problem. It came in the form of this plane, the very successful Focke-Wulf 190, known as the Butcher Bird. The 190 used the same BMW 801 radial engines envisioned for the new Arado transport. After the German failure at the Battle of Britain, there was no doubt that the new FW-90 had priority for the BMW engines. The Arado would have to look elsewhere for suitable power plants, but there were none with the same power as the BMW 801. To solve this problem, a 4-engine Millipede was proposed with a larger wing. This change led to delays. The end result was that possibly the best military transport of the Second World War was limited to a production run of less than 20 examples, leaving Auntie to soldier on alone. Eventually, almost 5,000 Ju-52s were made. Many continued to fly around the world for a number of years after the war, including some with the RAF. But Auntie was not their only Luftwaffe transport. 2 Arado 232 Millipedes were also flown by the Royal Air Force. During the course of World War II, German aircraft designers embraced many unusual concepts. Some worked, but not all. The Grumman P-163, a product of the mind of Richard Vogt, a German aircraft designer who conceived of many weird and wonderful designs during World War II. At a time when the shortage of aluminum was starting to affect aircraft production, the P163 concept offered a way of partially utilizing steel as an alternative, at least in a limited way. Of course, there would be a weight penalty. However, the additional strength of steel might allow the wings to support a crew gondola and each wingtip, thereby allowing much more free space in the main fuselage for engines, weapons, and fuel. Each of the gondolas would have weighed about 1 ton. Vogt predicted that they would actually improve flight performance by reducing both bending in the wings and turbulence from their outer edges. Project 163 was envisioned as a high-speed bomber, fulfilling some of the multiple roles performed by the famous Junkers JU-88. The Junkers plane was clearly in the fast bomber class. It had a crew of 3 or 4, grouped together to improve morale and enable better communication. However, the aircraft was lightly armed and relied mainly on speed for survival against enemy fighters. In contrast, the design of Blumenvoss's new proposal necessitated having 2 separate crew seating positions, separated by at least 60 feet. The 163 was manned by a crew of 4, with 2 men in each gondola. There would be a single pilot who would have a spectacular view, not disrupted by turning propellers. More significantly, the pilot sat back-to-back with his navigator and part-time gunner, who was in an excellent position to cover the rear and left flank of the aircraft. To balance the architecture, Project 163's other gondola had 2 gunners, one facing aft, the other forward. At least in theory, this high-speed bomber would have been very well protected. Not surprisingly, there were serious concerns about the actual control of such a revolutionary layout. How would a pilot react to being at the very tip of an aircraft rather than the center? To test the impact of this position on the pilot, an early asymmetric Vogt design was modified. An additional gondola was added to the BV-141's port wing and tested. Another major advantage of the wingtip cockpit was that it would leave the 163's main fuselage less cluttered, leaving space for a power plant that consisted of 2 engines coupled together, driving counter-rotating propellers in a center-line thrust. At about the same time that Project 163 was being developed, the center-line thrust approach was also being explored in the south of Germany by the Dornier Company. Their DO-335 Arrow heavy fighter bomber design was also based on the principle of center-line thrust. One engine set in the traditional nose position, and another placed in the center of the fuselage, driving a propeller at the very back of the aircraft. In the United States, another company, Douglas Aircraft, were also engrossed in another center-line thrust project, which was just as revolutionary. The XB-42, or Mixmaster, was designed as a fast, long-range bomber. It employed 2 engines mounted near the middle of the airframe, driving separate propellers grouped together at the rear. The XB-42's layout, like that of the DO-335, resulted in extremely clean flying surfaces that made for increased speed and maneuverability. Both aircraft were finally made, and with testing so advanced, they probably would have gone into production if the war had continued. Meanwhile, back in Germany, the war was not going well, and the benefits of all new aircraft projects were being seriously reappraised. Although it was reasonable to assume that Blumenvoss had a design that would be the equal of the Junkers JU-88 in speed and range, and it would also have offered considerably more defensive gunnery, there was still caution about the practicality of the crew positions. How would pilots feel about such an unusual design? The acid test would be the adapted 141 asymmetric plane. The standard BV-141 actually worked quite well. The addition of yet another gondola at the very tip of one wing made the aircraft even more bizarre looking, but it served its purpose and apparently proved that the wingtip cockpit arrangement was workable. However, workable just wasn't enough. Project 163 was cancelled before a prototype was built. There would be no armadas of this unusual-looking aircraft flying over enemy targets, and the addition of another gondola at the very tip of one wing did not turn it into